Okay, everyone, I think we actually are live now. It is actually 2 o'clock my time, Pacific Standard Time, actually Pacific Daylight Time, not standard any longer, and it is Sunday. And we actually have a very special guest with us today, a very prolific computer scientist by the name of Landon Curt Noll. He's an
Okay, everyone, I think we
eight-time
actually are live now.
record holder
Actually 2
for
o'clock
discovery
my
of
time,
prime
Pacific
numbers.
Standard
He also
Time.
has a
Actually
Pacific
background
Daylight Time,
in,
not standard astronomy, mathematics, cryptography, just about everything. He's had his finger in it. So, anyways, what I thought we'd kind of do is have an open Q&A. I do have the link to get in on my G Plus page. Anybody is invited. Just come on in. Of course, there will be some considerations, but come on in and you get to ask questions. If you want to talk about, computer science, you want to talk about, his work with astronomy, anything that from his Facebook page, you can go find that I've linked to his bio on the video description. So, come on in. Anyways, hey, Landon, nice to have you here with the Great Debate Community.
Thank you very much for inviting me on, and it's a pleasure. I always enjoy, talking about science and engaging in science. So this will be a fun thing. It looks like you got a good crew there, and of course, I should say a shout out to special friends of people like Red Eye and Nerdy and that darn Tranny and some other special folks I see in the chat room.
Yeah, thank you guys, and thank you, Red Eye. Red Eye actually made this happen, so I owe a special thanks to him. If I ever get a chance, I'll have a beer with him or just buy him a beer or something. Because we always like the fact that other people are going out there and finding great guests for us. It's difficult. It isn't always easy to find entertaining people and educated people to come on and have these types of discussions. I don't even know where to begin. I mean, we were off air before we started talking. I just found out you actually knew of G-Man, and I thought that was like the most interesting thing. I know people want to get into
I'm not
prime numbers.
I'm not a follower. I was a disclaimer on that, and it was Galen that actually introduced me, because Galen Alcyon is really big on going after people with logical fallacies. So,
and do you think that G-Man suffers from logical fallacy syndrome?
I think he certainly has a creative use of logic. He has a sort of own brand of logical constructions, and that sort of gets him into trouble. But it's entertaining for him, I suppose. So
it's entertaining for us too. I mean, my channel would survive without these guys, but every so often they say some interesting things, and we've got to put it on air. We got to talk about it, because this is like before we came live, we were discussing with you that. One of them was saying that the value of pi changes based upon the system of measurement you use. I mean, as a person who teaches mathematics, and which we'll get into in a second, what if one of your students, college level, advanced college level, somebody who's into like Calc 3, said something to you? Well, how would you respond to that?
Yeah, I would first ask them to explain and to demonstrate something like that, and to see whether or not the person is just picking up and parroting something, or they actually have some kind of construction that is that's surprising. For example, the common thing you'll hear, people say is, pi is this transcendental number, and it goes on for forever, never repeating. And if you're a smart ass, what you say is, no, there's actually a very compact form. Pi in base pi is 10. 2 digits, you're done, right? All I have to do is write it in base pi. Now, so when someone says something unusual like that, spend a little bit of time trying to figure out on what basis they're saying, and to see if there's anything interesting in that context. I know you see, 10 and base 10 is 10, or 5,000 and base 5,000 is 10. Pi and base pi is 10.
That's when I use Wolfram Alpha. Whenever we start changing bases, I'm going right to Wolfram Alpha and saying, okay, whatever that says, I'm going to go with that.
Right? But it gives you a teaching moment to say, well, what is really, when you see a number, what are you really seeing? And the answer is, you're seeing coefficients of a polynomial in, of products of powers of bases. So when you see 1, 2, 3, most people think, oh, you're dealing with base 10. So it's 1 times 10 to the second plus 2 times 10 to the first plus 3 times 10 to the 0. That's what that string of digits actually means. And there's no reason why you have to stick to base 10. In fact, computers oftentimes prefer bases that are a power of 2, because of their binary nature. So we just like 10, presumably because most of us have 10 fingers.
So it's arbitrary that we have base 10. pretty well. I wouldn't say arbitrary, but because we just so happen to have 10 digits that are easily accessible, not counting toes, we will use base 10.
Yeah, I suspect that they mean. I think the anthropologists might have something to say about that. Go ahead.
And didn't the Mesopotamians had a base 60 system?
Yes, and so in that sense, you know, anthropology is not my specialty field, but I would conjecture that a lot of people gravitated towards base 10 because of counting on digits. But I suspect you can go in and find other systems. I mean, the French system in counting in 20s is an example of a mixed radix system. So
if we had 12 fingers, we'd be like doing duodecimal.
Yeah, and some people like 12 because of the halves and thirds and whatnot. Presumably that in the old non-decimal British currency, the 12 pence, that was one of the things about being able to carve things up. But I'd say it's kind of a matter of convenience, but base 10 seemed to catch on for most of the world. Although again, I suspect there are plenty of counting systems that are not base 10 out there.
Yeah, and that's your area of expertise too. Because correct me if I'm wrong, but the prime numbers you deal with are literally a powers of 2, right? Minus 1 or something. Is that what it is?
Well, that's one of the types of numbers. A lot of the work that I've done in the last 2 decades have been on what's called Reitzel numbers, and they're h times 2 to the n minus 1. So they're a multiple of a power of 2 minus 1. Because there's a course I teach that basically says if you want to find a new largest known prime, a faster way of finding a new largest known prime is to look for primes of the form, some number times 2 to a power minus 1. The test for proving those are prime is only slightly more complex than the 2 to a power minus 1, but there are a lot more of them and they are a lot more frequent. So.
And do you have to have like some major computer power to actually deal with the numbers? Because you deal with very large numbers. I mean, you actually have named very large numbers yourself. Personally, have actually named them, right?
Yeah. So there's I'm credited along with Conway of developing extending the English names for numbers out to infinity. And that was actually an interesting thing in linguistics where we went back to the Latin that the English names were based upon, and actually we used the Latin of Venice and commercial Venice in the time of I think it's like the 14th, 15th centuries, and that's sort of where the old English names for numbers, and it's where you have things like the million, billion, trillion, quadrillion. That kind of stuff came from the Venetian Latin. And it's a slightly different Latin than the Vatican Latin. So one of the things that happens is you get Latin scholars coming and yelling at us saying, you did it wrong, you did it wrong, you did it wrong, and say, no, this is English, and it's based upon the Latin of Venice, and no, contrary to popular belief, Latin is a language that had evolved, and so there's some constructions that the commercial people in Venice used. Not that they were, into quadrillions of their currency, but they had the cardinal numbers and other systems that they were using in accounting that English borrowed from.
I remember. Go ahead. Go ahead.
Oh, I have a question regarding if most people are inclined to use a base 10 system, why did the Mesopotamians use a base 60? Or is there no reason for why they use that?
I mean, I'm not quite familiar with the I mean, I know that they had a base 60 and Babylonians also. In fact, our notion of the circle having 360 degrees really was paralleled with this notion that there were 300 at the time. There were 360 days was a nice round number in a year, right? And that even though there's 365, but either their measurements of the year were off, or it was one of those things where they found that 360 was a nicer number to work with than 365 and a quarter.
And we move about 1 degree on the orbit of the Earth
Yes.
around the sun.
Yeah, so that's sort of one of the uses of that was that in a day the positions of the stars will shift approximately 1 degree. Now, of course, in modern day stuff, it's a fraction. But if you're somebody trying to apply some sort of simplified model to your universe, 360 seemed a lot easier to construct. But again, there are certainly anthropologists that could give a much more detailed and probably accurate description of why they did a 60 and a 360 system.
How high are these numbers that we're talking about? I mean, I remember a long time ago reading things like arrow notation, which, these numbers are so high, they just have arrows that are used to notate. It's like transfinite kind of near infinity kind of things. I mean, can you kind of give to people so they wrap their head around these numbers of how vast these numbers really are?
Well, I mean, I like to think of it in terms of Latin powers, and but the system that we constructed can name can apply an English name to a number of any size. The thing that I found as a child was that I found dictionaries that showed the numbers up to 1 decillion, so that's 1 with 33 zeros after it, and that's a pretty practical number for everyday use. You have to a decillion things. You usually talk about something on a cosmic scale, or you're talking about something on atomic scale in macro size. And then some dictionaries went up to 1 bigtillion. So the thing that you notice about the English names is, why is it billion, trillion? Well, billion, bi, is the Latin root for 2. Trillion is tri, Latin root for 3. Quadrillion, the next one, is a Latin root for 4. Quintillion, 5. Sextillion, septillion, octillion, nontillion, decillion. And you find, hey, those names, where do those names come from? Well, they come from Latin. In fact, the English borrowed them from the commercial Latin at the time. The big commercial power when they borrowed it from was Venice. So that's why you get the Venetian Latin. On my website, there's a link to a CGI that drives a Perl program, and there's a Perl source that shows, so it's programmatically say this is how you can name a number of any particular size. And because I was frustrated as a kid that my knowledge of the numbers was limited. There's a story goes that when I was in kindergarten, so I was probably about 5 at the time, the teacher was doing sort of aptitude test and asked me in my aptitude test, well, how far can you count? And I said 999 decillion, 999 nontillion, 999 octillion, 999 septillion, 999 sextillion, 999 quintillion, 999 quadrillion, 909 trillion, 999 billion, 999 million, 999,999. And the only reason why I can't go higher is I don't know what the next thing beyond decillion is. And if you tell me, then I'll have another order of magnitude I can count. And she kind of looked at me like, what in the hell did you just say? One of those things. And so I thought that maybe I was not pronouncing them correctly. Because I had some of the ones like non-million, I wasn't quite sure on the pronunciation. So I went up the board and I actually went down, the nines, right? So we were talking about, it would have been 10 to the 36 power minus 1. And I wrote out the nines and just showed, say, da 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 da, right? And her reaction was, I don't believe you, start counting. And I guess as a kid, I either didn't appreciate the magnitude of it or just saw it as a challenge. So I sat down in the corner and started counting. And I could count, fairly fast. And it's fairly easy at some point, I was cycling through the hundreds of how to keep track of the thousands. And so I was using my fingers to keep track of the thousands. And I know that I decided that I use my legs for the 10,000s. So from what I can tell, I think I remember I counted up to 21,600 something or other. They sat me in the corner and for the entire day was sitting there counting. And she kind of came over there to see what I was doing and said, oh yeah, that's right. He's out there counting. And I slowed down enough to show her, that was 21,600, 21,601, 20,602, da 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 da, saying I can keep counting till cows come home. And she finally says, oh yes, that's right. We got to do this aptitude test thing. So she went over the paper and to the thing, how far can you count? She said over 100. And I thought that was actually rather insulting. I was actually rather insulted, and I said something rude enough to get sent to the principal's office.
Well, it wasn't a lie.
But it was like, I could hold my breath and count to 100. So it was like this notion, and I realized here was a teacher who didn't know the next Latin power beyond 1 decillion, right? So
is it vignetillion or something?
Well, you have the undecillion and dodecillion stuff.
Okay, so you'd have a decillion, then you have like un and duo and tre and quat and decillion, and then you
so you have to go through the teen.
Okay.
Vigtillion is the 20, and I can put into the link. There's a really nice Perl script. I mean, actually, you can run it. You can run it online. And it's to be able to name a number of any size, and
as you go on a higher level, you actually repeat the same pattern over and over again, or it's like a fractal, or not?
Yes. In fact, there's a page. I will post it first of all to the side chat over here. And then I can also post it in, I don't know, can I post?
Yeah, I'll add these links to the video description afterwards.
But that's basically a course, and it shows you about the counting system. And there you will see, on the table 1, you'll see undecillion, duodecillion, tridecillion, quadrodecillion, quintodecillion. It shows you the numbers. I do it for both the European and American system.
And it's funny is we actually have people in our community that get actually confused in double digits. So think I'm kidding.
But it's a thing that goes through and it takes you into the you're talking about 10 to the 300 to 10 to the 3,000 and all the way up, and shows you, and it gives you examples of numbers and breaks it down. And then of course there's an online program that you can do conversions and stuff. One of my things is whenever there's a new largest known prime, I generate the English name for it, just because somebody has to name it.
So they come to you and say, "Hey, what can we call this thing?" Because
I
super huge isn't really like too technical.
When I had the various records, one of the common things was asked of me is, well, how do you say that number, right?
We would call it BAFN. Figure out what that means.
But anyway, that page you posted shows you the thing of how to name it, and then if you're just lazy and want the computer to do it for you, this link. Oops, I'm sorry. This link that I'm.
So it really is a whole naming system. I mean, that can be applied to any number that they find. This system could be utilized to come up with how to describe it verbally.
Yes, okay. And I have to say, I have to thank my brother for that, because as a kid, I was just trying to, I was interested in numbers and I was trying to count. I was sort of trying to memorize, brute force the numbers. And as I recall, I had memorized up to like 117. And I saw some patterns, but didn't really think of me that there would be sort of a system of stuff. And so my brother, to have me stop bugging him, sat down and showed me the trick of how to count. And then of course we, after he knew, I think he knew up to a trillion or a quadrillion, and we went to the dictionary and found a table that allowed us to go up to decillion.
I should mention to people, I put it in the bio, but I should mention that you graduated from Cal State University, Hayward. I mean, you have a background in mathematics. You entered Linfield College. You got your bachelor's in cum laude. Is it cum laude? Yeah, cum laude, isn't
Yeah,
it?
yeah.
Yeah, in math and physics. But you did. Can I ask why you didn't go on to like maybe higher? Was it just? I mean, I looked at your
Well, I
your
looked at
resume. Oh my
at
God, I mean,
undergraduate
you've been
school
so
stuff, but
all over the place.
I think it was the lure of the Silicon Valley.
Gotcha.
You know, there, and I was already, and as one of the professors pointed out, one of my mentors, you're already publishing papers anyway, so you know why need to go through the hazing of graduate school.
I mean, you worked with everything.
My life would have turned out different had I gone into graduate school, but it hasn't slowed me down. I do recommend it for people.
Yeah, if you guys don't know, I mean, Landon has extensive background in Linux, in BSD, in DCOS. I mean, you any computer. It seems like you've worked with pretty much all the.
I was a very early a user of Linux, starting with the 5th edition. My father worked for the telephone company. My uncle worked at Bell Labs in Homedale, and we actually had teletype set up at our farm. So in '74, I was linking up to the machines at Bell Labs with the nice old 5th edition and 6th edition Unix, and really fell in love with the notion of the shell and how you construct and put things together to construct things of magnificent structure. I think is what really is. Even in other operating systems, I ended up going to something like the ZC NOS, building a shell like tool in order for me to do constructions of commands. And so I had the fortune of working with Unix early on. Was involved in standardization efforts. I think the wait PID system call was something I introduced to the Unix kernel, and really enjoyed. I really enjoyed this whole BSD side because it was the closest to the Bell Labs and was accessible. The Bell Labs is all that. That was when it was all encumbered by all that AT&T stuff.
I could barely get Ubuntu to work right half the time.
But as I say, that's sort of my I have a fondness for BSD type.
I envy that because I got to
systems.
tell you, I wish I would have stuck with my computer programming back in my. You're not that older than me, by the way. Back in when I remember in like the 70s, I was learning things like Focal, Fortran. We had punch tape. Punch tape. Who remembers punch tape? Right? We had actual punch tape.
I have stuff up in my lab. So
Yeah,
punch tape. Not a reader that works, but I've got punch tape.
But that was like really, low level programming, especially with like assembly and stuff like that. And I enjoyed that. I was like, this is really, like you said, it's the heart of the computer. This is the brains of the stuff you're working with. Yeah, got into Visual Basic and other high level stuff. And you know what? It's just, you forget all that stuff. I couldn't do assembly if my life depended on it at this point,
But I guess I like, from my attitude towards computers is that they're a tool, they're a means in not a means to something else, not in of themselves. So I was always using computers as a tool to discover. In fact, coined a term that Dr. Lamer had coined of experimental mathematics, experiments in math, was something I really fell in love with, because at the time of things like the ARPANET, that this teletype system at the farm was connected to, meant that I could use the ARPANET to go back to MIT, and there was this glorious machine there that ran this thing called Maxima that did all this symbolic algebra, and I could explore mathematics without the drudgery of getting all the signs and terms and so forth there. And so I started seeing things like integrate and differential equations, and started plotting them and seeing what they did, doing experiments and saying, what if I tweak this, what happens? What if I tweak this, what happens? And so having something like symbolic algebra system with Lisp that I could explore equations as objects and transform them and see what they do, push and pull the knobs and see how it responds, was a really important part of my mathematical development.
Wow, you're going way back if you're going back to Lisp.
Yeah, that's what the Maxima was written in Lisp, so you had to learn Lisp in order to really use it effectively. I mean, you could just run it straight away and do basic algebra stuff. But the real power of it is.
I want to inform that the chat is interested in the stuff about astronomy. So maybe
I'm taking note of the questions from the live chat. I am watching the live chat. If you're in the live chat, I'm not ignoring any of you guys out there. Trust me. I just figured we'd jump from one thing and go to another. I didn't know if anybody else had any more mathematical type questions to ask him. I saw one person ask if to have you explain why 1 equals 0.99 repeating.
Yeah.
Even though I've done a whole video on this, people. So I don't know why you don't watch my video on this, explaining in detail using calculus.
It's not very difficult.
No,
it's. I always find it curious that people have trouble with infinite things as opposed to accepting them for what they are. This notion of 9's going on forever. You asymptotically infinitely, asymptotically come infinitely close to 1. So it's 1. And so, but somehow some people have this notion everything has to be finite, everything has to be compact, everything is small, and this notion of an infinite
they're finite
set.
Yeah.
It's like, but if you just accept infinity as a thing, then infinite systems just like, okay, it's one of those things.
Yeah, I would just think it's even more simple than that. It's just 0.999 is just another way, or repeating is just another way of showing the same value. It's just an infinite repeating decimal. And and by the convergence of a sequence, it has to equal 1. I mean, that by definition.
What if you did 0.555 over and over again? What would it equal to?
0.555555.
For example.
That's going to be one of that's going to be it's going to be 5 over 90, right?
It's going to be 5 over 9.
Yes, 5 over 90.
5 over 9.
0. You said 0.55555 or?
Yes, it's over and over again. Yes.
Yeah. So 0.05555555 is the fraction 5 over 90.
Yeah, I thought you said 0.555. 0.55 would
be 0.55.
Yeah, so you did say 0.55.
Yeah, 5 nines. So it's the decimal approximation of there. But if you say 0.5 you're saying off to infinity, then that is 5 nines.
It's very counterintuitive. And it's also a thing that I have wondered about because our brains aren't easy to math. We have my own calculator can do calculations that my brain can't do very quickly, but my calculator can do it in milliseconds.
See, I was so
impressed. So that's
Cantor being able to come up with this thing, his cardinalities. How do you think like that? That takes a whole different level.
you've got to. I think the big thing that is important in dealing with things, these transfinite stuff, is to accept infinity as an object in and of itself, rather than trying to treat infinity as finite. And I think, and people run into problems just like they're trying to conceive the universe as opposed to accepting it for what it is, and exploring it. This notion I got to wrap my head around infinity. No, infinity is there whether your head wraps around it or not. Accept it, deal with it, and use it effectively. That's a much more effective way.
Some people claim that actual infinities, like an infinite past, can't exist.
Well, it's an interesting question about in terms of time, of whether time is a beginning or not, and that's where you're getting into physics and cosmology, which is sort of, I guess, to a parallel to. I'm a planetary scientist, so I study planets, both our planet and as well as planets in our solar system and planets outside our solar system. And in order to really understand planets, you have to understand, how they evolve, how the universe generates planets, and that means you have to study star systems. You have to study the birth and death of star systems. You have to study galaxies. You have to go back to the Big Bang and the processes that lead up to building, to generating planets. And so, I like to say, planets are sort of the culmination of a lot of physics in the universe. Now, some of my colleagues that are more cosmologists refer to me as a short-sighted astronomer, because I typically planets are relatively close. I mean, the ones we can detect are relatively close, and they're dealing with things on the visible edge. But I remind them that one of the nice byproducts of all that Big Bang stuff they generate is planets, and particularly this planet. And this discussion that we have is culmination of lots of physics.
Are you more of an A theorist in time or B theorist?
A theorist or B theorist? I don't understand the.
It's how we look at time, whether it happens all at once or we're just like in a slideshow of time and we're just taking a slice out of it. That there is really no future or past. It's that there's knowledge that exists, but we know of the past because we experienced it. We haven't experienced the future yet, but we do know that the future exists.
So the future and the past and the present are equally
together
real.
at once. We're just living a small section. We're in the present, which happens to be just where we're at, but the present and the past and future already exist.
I mean, in physics, time is a fairly complex subject, and the arrow of time, we would say, is really bound up in this notion of causality, and is bound up in the things like second law, or the dynamics of things going forward.
Mm-hmm.
And but if you look at the mathematics of how we describe it, the mathematics does not prohibit backwards time. However, and this is a very important point, the universe does not ask your permission to do what it does. So just because you get some mathematical model that says time should go backwards and forwards doesn't mean the universe gives a damn about that model, right? We use math to try to describe what we think the universe is doing, but the universe does what it does. And so just because the math says time can reverse, go backwards, we can jump back in time, doesn't mean we can. It may mean that our math is describing something which is not physical. But it's time is one of those fairly deep subjects in physics that's quite fun. But again, if you're someone like me that's studying planets and how planets are formed, how planets evolve, time is one of those factors, as well as lots of great physics that goes into it.
So how long is the time to create your average planet? Because as you know, I do talk about, because I discuss with you, I talk about debunking Earth creationism a lot, and that planetary formation and the universe cannot be 7,000 years old. It's just unimaginably impossible.
Yeah.
And sort of planetary person, I mean, what is the quickest a planet could probably form? A solid planet, not gases, where it's just a bunch of gas coming to coalesce. But I mean, an actual solid core planet. How long would that take?
From the average nebular cloud.
Yeah. I mean, if our model of how planets form is reasonably correct, that model suggests that planets can, terrestrial type planets can form on the order of between 10 and 100 million years. It kind of depends upon the circumstance of the thing, and some people think that it can actually form a lot quicker. The model that is commonly invoked is if you've got some dust cloud or dust ring around us, presumably a star, that dust begins to congeal and accrete into small objects. Those small objects begin to gravitationally attract and build up to larger and larger planetesimals. Yeah.
It's a snowball.
The gravity of that sucks up things around the ring, builds a gap, and forms.
Is that usually caused by some kind of perturbation in the nebula itself? Something that may have caused a wave in the nebula to cause that initial nucleation of a planet?
Like a neighboring supernova.
Or something to cause a shock wave.
Well, usually, if you talk about how the material begins to create in the first place, for example, in our solar system, the model we currently use is that there were two supernovae that occurred about 4.8 billion years ago, and another one 4.7 billion years ago. And when a massive star, the death of a massive star, does something really amazing, which is it builds up much of the heavier elements. So much of you that's not hydrogen is built on nuclei that came from the death of a previous star. So not only does the star create this significant shock wave to blast stuff out, but the forces involved build much more complex atoms. So it sends out this shower of dust, of material.
We are all star stuff.
Yes.
Yeah. Yes.
Yeah.
So, in all your studies of planetary formation, have you ever seen one actually produce a flat disk shape?
Well, there's that curious thing about Pan.
That might
Very
be.
funny,
You know what?
Steve.
I don't say that in jest. I mean, not the flat Earth
Look at
model
the image
that we
of
get
Pan.
posed. Yeah.
Look at the image of Pan, the moon around Saturn.
Mm-hmm.
It looks like a pasta. So it looks like a tortellini.
Mm-hmm.
And it was one of those things where, and this is a delightful thing. It's one of those things where we got really excited because we said, what the heck is that and how does that form? See, scientists get really, really enjoy when they realize they don't know something, because realizing, admitting you don't know something is the beginning of a path to knowledge. So when we saw, and go look up on the web, Pan, P-A-N, so you might have to say Pan, moon of Saturn to not get pots and pans stuff. You'll see this really weird moonlet. Now this moonlet it was discovered because it was there was a gap in the rings around Saturn, since the planet has those nice rings, and there's one little gap, and inside that gap is this moon that was going around, and it appears the rings of Saturn are very thin. I mean, they're measured in meters to maybe 100 meters thick, so they're a very, very thin structure. And this moon Pan is about 13 kilometers. So you've got this ball with this ring dust, going through the center of the plane, and the result is it's got this flange that looks like a pasta tortellini. And we really said, wow, we didn't know that planets can do that. So
it does look like tortellini, by the way. And here's my argument, Landon. How about this? Since it looks like a tortellini, and humans have created tortellini, ergo it was intelligently designed.
Well, this is obviously evidence for the flying
Argument
spaghetti
energy.
monster.
Yes.
Yeah, pastafarians would love.
Can you get any more concrete evidence of
a
that?
pastafarian deity? Yeah.
It's right to make another dish other than pasta.
Yeah, but you see that's one of the things again about science that is maybe not always understood, is that science is about questions. It's not about answers. And science really values the question. That's how the work is on. And science gets really excited when we find something unexpected that we don't understand. And that's the people who are the greats in science are the people that ask the right questions of the right people at the right time.
And that's why it's kind of funny when we have people in our community that say things like, "Oh, well, scientists have been hiding the truth, or they don't want to admit that this is wrong, or they don't want to find out that their models are not correct." And I've always been saying from day one that that's completely just the opposite. I mean, for a scientist, the greatest thing you can do is falsify a model. Yeah. I mean, if you could disprove
the most.
Hang on, no,
go for it.
If you could disprove the theory of evolution or the theory of gravity, general relativity, I mean, think how your name would be immortalized.
Yeah,
and the most famous scientists ever known have done that. Einstein, Darwin, Newton, Pasteur.
Yeah, I mean, Einstein didn't falsify Newton, but he sure showed that Newtonian physics wasn't applicable in all circumstances.
And so realizing you don't know something, admitting it, and then working to try to understand it and try to answer that question. But then the wonderful thing is that typically when you do that, you generate more questions. That's kind of the wonderful thing about the built-in lifetime enjoyment of science, is that there's always more questions, assuming you don't close your mind. And it's a very different thing than, let's say, theology, which tries to give you answers. Science really tries to give you questions.
Yeah, and I'm fine with people that have theological beliefs. It's just when they encroach on the scientific realm, especially when their belief is a presupposition that takes precedence. That's when you're no longer in the scientific arena. That's when you're
exactly. Mm-hmm. And notice, for example, when I was talking about planet formation, I said things like, if our model of planet formation is reasonably correct. and it appears to be. I didn't say this is truth. Here's the dogma. Your article of faith says blah 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 blah. No, it's here's our current, and believe me, we're looking for counterexamples. We're looking for way or things to refine and shape our notion. When I went to college and was studying cosmology at the time, the big debate was whether the universe was open or closed, whether the universe was going to expand. We knew the universe was expanding, but it was going to expand, halt, come back in this giant crunch, or it was going to expand forever, right? Open and close. And that was actually a relatively radical debate. And what we didn't realize was it was neither. It was accelerating. It's this thing called dark energy. In fact, my T-shirt it was coined about that. And so it wasn't that I wasted my time in sitting in physics lectures learning about open and closed universes. It was that when it came time to, and people like Reese and Filipinko showed the universe was accelerating, I had the ability to appreciate just how little about the universe I knew. And I think that it just opened it's opened this vast new area of study of stuff, because it generated tremendous questions. And for someone like me, a planetary scientist, the processes of dark energy and this other thing called dark matter are really fundamental to how galaxies form, and which is fundamental to how stars form, which is fundamental to how planetary systems form.
I have a question about it. I have read that some people suspect, or some scientists suspect, that dark energy is like this quantum vacuum pressure. That like when particles popping in and out of existence, and this creates this pressure of dark energy. Or are there other hypotheses of what dark energy might be?
Yeah, the problem with that quantum vacuum thing, and what he's talking about, is the fact that quantum mechanics, I guess in a layman's term, does not like you to pin down exact things. And so one of the exact things you can't pin down is here is nothing, and the energy is nothing, right? Quantum mechanics says no. There are, in fact, in this thing of nothing, there actually are particles popping in and out of existence, annihilating each other. And you can actually do experiments where you can take two plates in a vacuum very close to each other in parallel and measure the force of those quantum fluctuations pushing on the plates. It's an extraordinary result, but it's one of those weirdnesses of.
Is that dark? Is it the dark energy that's pushing out?
The problem is that
Casimir effect is what it's called.
That's a Casimir effect. Yeah, and I look forward. Go on the web or on YouTube and look up Casimir effect. It's a really amazing thing. But the problem is that force is about 120 orders of magnitude off from what you need for dark energy. That would be a logical thing. Yes. And if the universe was nice and rational, in my mind, or simple, that would have been the case. But it turns out it's not. It is. The best we can tell right now about dark energy is that it appears to be a property of space, and that it appears to be something which is currently repulsive. It may be repulsive all the time. We don't quite know.
And space doesn't have a quantum mechanical basis yet. Yes. Like electricity and the weak and strong nuclear forces have.
Yeah, and Einstein, I think, knew about this. I mean, obviously he had the cosmological constant, which is basically dark energy on just different signage. But I mean, we have known that this force existed. Or at least it was allowed.
Einstein's big thing was he preferred the model of the steady state universe. The universe has always been here, but if you have this universe already been here and you got all this stuff of gravity, why isn't the universe collapsing in on itself, right? Why? That's essentially what Einstein observed. You have all these stars and galaxies and stuff out there with gravity. The universe should be pulling in on itself and collapsing to a point. It's not. So how do you make the universe appear to be steady and stable structure? And the answer was his fudge factor, the cosmological constant, which when Hubble showed the universe was accelerating, then the assumption Einstein made, well, it was a plausible assumption at the time as well, I don't need this fudge factor. The universe is accelerating. or expanding, I should say, is expanding. And that expanding is counteracting gravity, right? Was the assumption that the expanding of the universe was counteracting the gravitational force, and that the things were balanced. And of course, we later learned that that was not the case. But that's, again, very important in understanding the universe, how the largest structures are made, how those structures end up integrated in galaxies. And in fact, in the history of the universe, I would say probably one of the biggest problems that astronomy is facing, or one of the biggest problems, is how galaxies form.
Really?
As a young student, the assumption was galaxies were the complex structures that took several billion years to form. But with observations, we find galaxies that are forming earlier and earlier and earlier. And one of the questions is, did the first galaxies form from a gas cloud collapsing in on itself, and then stars form from the gas cloud, or was it a early collection of stars that came together to form a galaxy, or was it first population stars that were massive, that had giant supernovas, and those shock waves went out and collapsed clouds to form galaxies? Which came first, the galaxy, or the cloud, or did stars merge together to form a galaxy, or some combination of the two?
And does the formation have something to do with the fact that most galaxies, if not all, have supermassive black holes inside the center?
Yes, and one of the things is that do those black holes form while the galaxy is forming, or do the galaxies form around black holes?
What
Before
are the
the
very
black
earliest
holes,
ones have
primordial. Most galaxies that are center have a black hole.
Yeah, but the very earliest ones, because I mean, we literally have pushed the limits on the earliest detection of black.
And that's a really
galaxies.
important
I
point.
mean, seriously, to the point is
We don't know.
Yeah. Mm-hmm.
We don't know. One of the things that, and this is one of the really important topics for the James Webb Telescope, infrared telescope, or the Square Comet Array radio telescope, is going to be detecting the formation of the first galaxies.
I have seen a simulation called Illustris that simulated the development of the universe from the start to today. Didn't that show kind of how maybe galaxies could have formed?
Yes, and there are some great simulations that produce universe-like structures. You got to be careful that simulations only give you insights. They're not saying this is how it actually.
Yes.
Works.
That's why I said that could have, or maybe could have.
Yeah. And I agree with you on that. It was actually kind of fun to realize that the physics we were studying mostly, and talking about particles and nuclei and photons and neutrinos, all this stuff, ended up being only about 4% of the universe. That is somewhere around 24 to 26% is this stuff which we can detect by its gravitational field. So presuming it has mass and is warping space. But that's about all we can detect from it. This stuff appears to have no interaction with light, or what that we can tell. So this substance does not reflect light. It doesn't absorb light. It doesn't transmit light. It doesn't appear to have a temperature. It just is. And it turned out there's about 6 times more of that stuff than normal stuff. Whatever it is. And then when the dark energy came around, and we found that somewhere north, about 70% of the universe was this force that has it behaves as if it's a property of space. And as the universe expands, you get more volume, more space, and the force is taking over and dominating the universe. We're accelerating rather than decelerating or coasting, and that was a really surprising thing. So it's warning to say that you have these models. You got to be careful that you don't confuse the model with reality. But again,
it amazes me that you have people that every time we come up with a scientific discovery, they're like, oh, well, science has changed. And it's like, yes, science learns from things it learns before, right? I mean, when I was growing up, the thought the accelerated universe was not existent. I mean, what was it, the early 90s that was discovered?
Yes.
Yeah.
And so, and yes, and in fact, this T-shirt, by the way, was I did some work for and helped the team, the two teams that got the Nobel Prize, awarded Nobel Prize, although they only awarded 3 individual, but was awarded to the discovery of the 2 teams that showed the existence of dark energy. And so all the the team members, Nobel team members got this shirt. The King of Sweden got this shirt, and I have it. So it's sort of one of my special physics shirts. But it was a case where we were asking the right questions, and the questions that both teams were asking was, we want to measure the expansion rate of the universe and see whether the expansion rate is consistent, right? And getting longer and longer baseline. How do we do that? By looking for things called type 1a supernovae, which are intrinsically about the same brightness, measuring their distance and measuring the brightness to understand how much the universe has grown. And in particular, significant credit goes to Adam Rees, because he was a graduate student, stuck with the task of the grunt work of doing all the calculations to say, this is the rate at which the universe is expanding. And he kept coming up with really absurd numbers. And it kind of depended upon which data set of whether the curve was like this, curve like this, curve like this. And it turned out, in fact, it's actually this weird saddle curve. He came to his advisor and said, the data we have is not linear. It's got this weird curve, and it appears to be going faster and faster now, and it's slower back then, and it turned a corner around 5 billion years ago. And of course, the advisor said, well, that's absurd. You probably did something wrong. Go back and find your error and fix it. And he did it several times, and he could have just said, well, I'm going to ignore these data points because they're not convenient, ignore these data points, draw the straight line and be done. But he said, no, the data shows this wobble. We've got something wrong with our we don't understand the results of our experiment. Something must be wrong. Well, the California group had also a counterpart was in Australia doing the same thing and coming up with absurd numbers. But because he stuck to his gun, stuck to the scientific process, they ended up both publishing in the same the same journal this absurd result, which now we have at least 4 independent ways of verifying that most of the universe is this dark energy thing, and that's got to have a fundamental factor on how galaxies form. And the dark energy and dark matter are really fundamental to galaxy formation, and probably some of the problems we had in trying to figure out how galaxies form in the first place is because we didn't really have a good handle about dark energy or dark matter. Not that we have a great handle right now. There's still lots of questions, but fundamentally, 96% of the universe is these 2 things. So it's probably really important to understand those things before you begin to have a really good handle on how stuff evolves.
Yeah, the specifics of them are obviously there's questions about there, but there's no doubt that both dark matter and dark energy exist. There's no question. I mean, dark energy is a force that we see causing universal acceleration. Whatever it is, something is causing that to happen. And dark matter, obviously, we can see the gravitational effects in galaxies, right? We see the distortions. Something's causing it, and it's not emitting photons. It doesn't emit light. So and
so now I should say we have never detected it emitting photons. We've never detected it absorbing or so not reflections, no absorption, no emission, right? Now, is it very, very weakly interacting, and it's so interacting we can't detect it? That's getting very pretty hard to accept. But probably the best structure that we've seen, best evidence is the bullet cluster. It's a cluster of galaxies, and a typically image shows you the cluster of galaxies that move through pass through each other. It shows X-ray glow from the gas clouds that got stripped when these 2 cluster of galaxies pass through each other. The gas clouds slammed together and kind of had a high temperature interaction, stripping it of the most of the material that was in between galaxies. And it also shows you, there's a blue part of the component showing you the lensing effect, the gravitational field, because distant galaxies behind it are lensed, the light is bent. So we can tell where the mass, we're told where the gravitational field is. And the gravitational field is much more massive than the glowing bits of the galaxies that you can see. We can count the galaxies, you can count its mass, and you find that the distortion is much stronger, in fact, about 6 times more mass than there is of stuff. It from the bullet cluster, the sort of the thing about one part is in stars, in glowing stars and galaxies, and 4 parts are material that are not yet stars, cold material, and 24 parts is this dark matter stuff, which has mass or has a gravitational field, but other than that, we don't know what it is. It's kind of embarrassing that it is, but again, we're really excited because we don't know something, and it's generating great questions for which I think we will discover some amazing things about our universe.
Well, science is always asking those questions. Science is always looking for more questions to answer. We're never going to run out of questions, right? It's just never going to happen. Brandon, do you want to ask a question?
Is dark matter a new particle to be discovered?
That's been one of the hopes that the particle physicists came up with, because in particle physics we have the standard model, which is a really nice mathematical structure that we think describes physics at the subatomic level, and the Higgs boson was one of the key missing pieces that was presumably discovered recently. The problem is the standard model doesn't really have a convenient way to say, and here's this dark matter stuff. There's something called supersymmetry that some particle physicists hope will be the reason for dark matter, but so far places like CERN and places like Fermilab have failed to detect dark matter. There's been experiments underground to see if dark matter somehow weakly interacts with matter, to be able to catch those weakly interactions on things like the Xenon 100, these chambers that are deep underground to protect themselves from radiation from space. And they failed to find dark matter, which is kind of embarrassing, given that there's much more dark matter than there is normal stuff. And yet it'd be really sad if it was just like, yes, we happen to be some desert of dark matter for some reason. That would be really unfortunate.
So what is the prevailing? I mean, do they think dark matter is WIMPs? Do they think it's strangelets? Do they think it's a force carrier for dark photons, a force carrier? I mean, there's baryonic, is it non-baryonic? There's so many different things that I've seen on these dark matter theories. I mean, I think the current one is lambda CDM is the most prevalent.
Yeah, I would be surprised if it was baryonic matter, simply because one would expect baryonic matter to show up in the electromagnetic spectrum. Mm-hmm. You'd find forces that are there. You'd find magnetic fields. You'd find polarization. You'd think, right? But of course, you could have weird baryonic matter we don't understand, and that could lead us there. When people like Zwicky were pointing out that galaxies were spinning too fast to stay in their structure, and the cluster of the galaxies were orbiting each other too fast to stay in their structure, there had to be some hidden mass. Various people came up with excuses saying, well, it's probably black holes there we can't see. Maybe neutrinos have mass and it's there. And it turned out, no. It's the only thing we know is the existence of these gravitational fields that have a really important role to play in galaxies. And the structure of galaxies, particularly when you have that much mass around, is going to really shape how bars and arms of galaxies form. So when you're trying to understand how galaxies, and I mentioned, again, we have a big problem of how galaxies evolve. Understanding dark matter and its effect is of fundamental importance.
One of the things that younger creationists bring up actually is that we don't understand spiral galaxies very well. and their formation. And we do know, again, that dark matter does exist, what it is. And I agree, I don't think it's baryonic matter either. I just don't. But how do you respond to people when they say, oh, look, we have a discrepancy here, ergo, the Earth must be 7,000 years old? I mean...
I would say that science is about questions. And if you have problems with questions, you don't want to go anywhere near science, because that's what it values. Science actually values questions more than answers. Answers are merely temporary stopgaps to the next set of questions. So if you want your dogma and everything answered for you, use faith and religion, that sort of thing, fine. But if you want questions, and really serious discussion about those questions and attempt to answer those questions, then it's science. So the fact that we don't know something is saying, yes, it's a scientific process, right? And the people 500 years ago, we can look to say, well, gee, they didn't understand this and this. People 500 years from now will look at us and see, wow, they didn't understand and now we do.
Right.
But the questions what would amaze me is to understand what kind of questions they're asking 500 years from now. That would be
amazing.
That would be something I'd really.
See, I don't believe in time travel. I don't believe you go backwards in time. I know Feynman has in his lecture notes. I understand that certain particles, when they're created, will go backwards in time and one will go forward. I get that, but it's usually on a Planck scale. It's really on a little
but that business about antimatter traveling back in time, that's a model.
Yes, it's a model.
It doesn't mean that the antimatter particles go backwards, right?
Right, exactly. Mm-hmm. Yeah, and people take these models very hyper literally sometimes, but but I do know that you can go forward in time as much as you want. I mean, we have the technology to send people that far based on relativity. We could send them very, very fast and they come back 500 years from now. And I was thinking to myself, I would love to do that if I didn't have my daughter and all you lovely people out there that watch my stuff. I mean, you couldn't come back, right? So you couldn't come back and tell anybody anything. Yeah. But can you imagine going?
But I would take the one trip just to figure out. I think when I got off the bus, right, the time travel 500 years from now, and got off the bus, what questions would you start asking? Right, I have my step. What would you immediately start asking?
You'd be a caveman, though. If you were 500,000 years in the future, you'd be like a Neanderthal.
Let's say 500. Let's say 500 years.
That's reasonable. Oh, I can imagine the technology would have there. I mean, we're on the cusp of quantum.
I would closely understand. One of the first things I would say is the extended Riemann hypothesis true or false?
Which hypothesis?
Right. The Riemann hypothesis.
Oh, the Riemann hypothesis. Oh, yeah. That's $1 million.
I want to know. First of all, that has that been resolved?
Yeah.
And is it true or false? Right. Because that's one of the big linchpins in number theory.
Problem, yeah.
Yeah. And it's probably there's probably more things pending on the yes or no of that question in number theory than anything else.
And that would be equals NP.
Well, what is the Riemann hypothesis?
Go ahead and explain the Riemann hypothesis. I know what it is, but I couldn't even begin to explain like you do. But
there's a thing called a zeta function, which is basically an infinite sum of complex numbers. So it's a sum or reciprocal of powers of complex numbers. And the Riemann hypothesis, there are certain of those sums that sum to zero, right? Obviously, if you sum all the powers of the complex number zero, you'll get zero, right? There's trivial zeros, right? And on the plane, there's the even numbers, negative numbers going that way. There are well-known planes beyond one, but on the complex plane between 0 and 1, where the real numbers between 0 and 1, Riemann hypothesis says that the zeros lie along the 1/2 line. But if you have a zero that's non-trivial, it's going to be on that the real component will be 1/2. It appears to be the case. We found trillions of zeros along that line. We've never found one off the line. Never found a complex thing, but it has a lot to do with density of primes. Has a lot to do with complex constructions, and there's a lot of things that are resting on it, whether it's true or not. So that would be one of the questions.
Now, when they're trying to prove that, though, are they actually trying to find a non-trivial zero on the 0.5, or are they trying to find an example of a non-trivial zero not on the 0.5?
Well, if it's again non-trivial zeros have to do with stuff beyond 1, the negative even numbers are beyond below 0. The strip in the middle between 0 and 1, that's where the non-trivial points are.
Okay, so
if you find a zero which does not have a real component of 1/2, then the Riemann hypothesis is false.
It's false. Okay, so all they got to do is find one instance of that.
Yes. Now, but of course, you know, there's been deep computer searches. That doesn't say that whether it's true or not. It just means that it's not easy to find a counterexample.
Is it? Do you think it's provable though? Do you think it's provable without finding a counterexample? Do you think they could actually prove it where you could never find a counterexample?
I certainly hope it's provable. It would be disappointing if it's one of those unprovable things. But that's one of the things. So that's why I'd ask, you know, has the Riemann hypothesis been settled? I think I'd also want to know whether the Collex conjecture is true or false. It would be probably one of those things because I'm partial to that. This is the so-called 3n + 1 problem.
Still not familiar with
you take an integer, let's say greater than 1. If it's even, divide by 2. If it's odd, multiply it by 3 and add 1. Right? So let's take a number. Like that. Let's take the number 5. 5 is odd. So you multiply 3, add 1, you get 16. 16 is even. You divide by 2 is 8. 8's even. 4, 2, 1. Now the Collex conjecture says, do all integers, you know, greater than 1 eventually lead back to 1. Right? So if you take the number 20, 20 is even, so you get 10. 10 is even, so you get 5. 5 goes to 16. You know, and it collapses, you know, 8, 4, 2, 1. Right? It appears that all numbers go back to all numbers greater than 1 lead back to 1. Now, a counterexample would be is if for some reason you get looped, you go up high and you get stuck in a loop and you never can leave, or you take off to infinity.
So it explodes without bound, or it goes back to 1.
Yes.
Okay.
Or getting stuck in some cycle.
I do remember. I think Numberphile had something on that.
And I remember, you know, that it was that, you know, the Eredish, this great mathematician, told me that, you know, he said that mathematics does not yet have the tools necessary to answer this question. There's a lot of groundwork has to be laid before that, and that's a very fundamental property of the number system, to which you know, people are trying. So it'll be one of the math questions.
This might be way out there. But what have you familiarized yourself with the thing on YouTube? It's become a big thing that if you do analytical continuation where you take a summation of 1 + 2 + 3 + 4, and you don't do it as a divergent series, you basically get -1/12.
Yeah, these are these infinite sets.
Using Riemann functions, right? So I mean, what's your stance on that? Because I mean, I know a lot of mathematicians, and I got to tell you, they're all over the board on this particular one. Whether they're like, oh yeah, it's legit, it's analytical continuation, or other ones are like, oh no, they're just just abuse of the Riemann. I can't pronounce that guy's name. Summation. So what do you think about it? I mean, would you say that it's valid if you use it for what it's for?
I mean, yeah. I mean, in terms of yes, it's valid if you use it, but I think the thing you have to do is you have to be very careful about the way you ask the question. You know, that's where I think people run into problems. If you sit there and you say, you know, is the sum of increasing integers less than 0, versus, you know, versus, you know, is this particular summation series convergent, right? Those are subtly different questions. Mm-hmm. And I think where some people get objection is that they apply it in a manner. But you know, the math to derive the cute -1/12, you know, is real stuff. It's not it's not, you know, some sleight of hand trick. So just that you have to be very careful about how you ask the question.
It has application too.
So the big
orbitals.
Sorry,
that's okay. I was just gonna say
the big question is.
Go ahead, Brenda.
Oh, so the big question is, when are you going to have a show on Numberphile?
I've thought about that, and one of the things in particular that we've been talking about is doing something on Riesel tests and numbers of that form. But you know, I haven't been invited yet, but it would be a great pleasure to do something. I would probably talk about, you know, either primality testing of large numbers, how one goes about testing the primality of numbers, and the quick answer is primality testing has very little to do with breaking a number down into its common factors. Factoring and primality only intersect at the sort of degenerate case of proof of primality by exhaustively searching for factors. Most of primality testing says, here's a property that only primes have. This number has that property. Therefore, this number is prime. That's essentially.
You should get a hold of Dr. James Grind. James Grind. He's actually known as Singing Banana. He actually has been with Numberphile off and on. I actually have communicated with him before because I posted a long time ago on why 1 = 0.9 repeating and stuff like that. That would be the guy to talk to. I mean,
we did another thing about, I did something, submitted something about, why 1 is not considered prime, and that's sort of a history of.
It's not prime. Yeah, it's not prime.
Yes. Although, there was a history at a period of time when it was considered prime.
Yeah, well, there was a period of time where we didn't take irrationals existing either.
Well, I mean, but in terms of that, but in terms of what you're saying, the history of 1 as prime. I mean, most of the history of 1 is based upon is that it's not prime, but if it in fact, if you look at literature, right, and so again, we're not talking about and or we're saying that almost nobody on record defined 1 as prime until Stefan in 1585. And from the sort of the mid 18th century to the start of the 20th century, there were many that referred 1 to be as being prime, but commonly today it's not. There's I think the last, if you talk about professional mathematician that considered 1 to be prime, died in like 1930 or something. So the period of 1 being prime only really lasted from mid 18th century to mid 20th century, with the first written record at 1585. Now it's not, and so it comes down to what is a mathematical definition, and a pragmatic answer is I like to say a mathematical definition is something that mathematical community generally agrees upon.
Yeah.
Yeah.
Who decides what the who decides what the number 2 means?
Yeah. Hey, Landon, I've got
Hi,
two
Chris.
questions for you.
Yeah, hi, Chris.
Sure. Hey, how's it going?
Yeah, welcome, buddy.
I've actually got about 10 questions for you, but I'll ask the relevant ones right now.
He'd probably like to go to sleep at some time and eat, and so. But go ahead.
No,
we'll keep you all day, man.
We
do this 8 hours a day.
So,
I'm doing fine.
Go ahead.
Okay, so on the Riemann hypothesis and the whole summing numbers to get -12, I'm given to understand that that's a fairly important thing, a fairly important part of calculating the number of dimensions in string theory. So my first question is my understanding that it's important in string theory correct? And my second part of that is, if they did manage to find zeros that are off the number line, would that require a big revision to string theory?
I don't think so. I think that the Riemann hypothesis, the question of the Riemann hypothesis is independent of the so-called string theory. The business about the kind of mathematics that one uses in playing around with strings requires you to be able to handle some of these, infinities and infinite sums. So the kind of mathematics that leads to that -1/12 is the type of thing that's rich within string mathematics. As a physicist, I have trouble giving strings the level of theory. One of the big things about theory is it's got to be falsifiable.
Oh, sure. Now let's call it a string model.
And in fact, it's not. So I call it string hypothesis. So I object to the string theory. But string mathematics is very interesting. And in fact, string mathematics is real. Whether it has anything to do with the universe is another question. And when you're looking at string mathematics, you're dealing with a lot of this. There's a lot of infinite sums, and things like that result of -1/12 is an example of something.
Okay.
But as far as I know, the question of Riemann hypothesis is independent the validity of string mathematics.
I'm reading The Cosmic Landscape right now by Leonard Susskind. He's obviously a huge advocate.
Yeah, really great.
Yeah, huge advocate.
Great guy.
Oh, yeah. If I could get him on, my life would be complete. I mean, he's just so fabulous. But yeah, the book is really good. Actually, Lamed got it for me. Thank you, Lamed student. And I am enjoying it. Eventually finish it. But he makes a wonderful case for it, even though, again, I think what you said, it's not a theory. It's a conjecture, hypothesis. Now there is obviously mathematics, but I don't like the term theory.
It's yet to say we're this theory is falsifiable if you find blah 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 blah. That's and now I'm not saying that the string mathematics and string hypothesis is worthless. There are some really great people, and I hope they're successful because it's got some really interesting mathematics, and if it has something to do with reality, that would be amazing. And so it's a worthwhile endeavor. You just have to do a little bit of growing up. So maybe in the question I would ask in my 500 years from now off the bus is, are you using string theory today to describe the universe?
Yeah, I mean,
So-
huge ramifications if it is true, though. I mean, with he calls it the megaverse, right? Can you imagine living in just one of multiple universes, complete universes?
Yeah. Well, one of my favorite expressions is that I live in my favorite universe.
Because you're in it.
And yeah, well, and it's my favorite, right? So, and I'm not ruling out the multiverse. It's just that this one happens to be my favorite of all the ones.
So Landon, I've been thinking recently about the universe as basically a great big thing that's calculating itself. Okay, I mean, there are events going on. Well, I was thinking that if any truly analog physics existed in our universe, that would mean that in the tiniest of events, there would be an infinite amount of calculation, which seems to me an extravagant claim. So is the inescapable conclusion, if there were truly analog quantities in the universe, that there's infinite calculation going into things?
Well, I mean, in some ways, if that calculation converges, you can have, there certainly are infinite series that converge to nice finite numbers, right? The sum of the reciprocals of the power of 2 show up as 2 quite nicely. So it's not, or 1 depending on when you start. So it's not that the presence of infinities is demands or invalidates the digital thing. Because the other for people to understand, the other state question is the universe just a giant sort of digital state machine? And what we see is that where we have these things, these Planck lengths and Planck times and Planck masses, and it's just built up on that granular scale. But those things are so tiny that when we're sitting above, even in atomic space, that all looks continuous. But in fact, it's discrete, and it's an intriguing question. There's been some results that have failed to confirm sort of the digital understructure or the granular understructure of space. It doesn't mean that it has evolved. So for example, if you have photons that are extraordinarily energetic, and these photons become have wavelengths that start to approach the grain of space, if space is granular, then you will, or multiple that, you will start to see photons moving through space at different speeds. You've got normal photons that we deal with. The wavelengths are so huge compared with any quantization of space that we don't see the effect. But if you had a photon that was, let's say, 1.1, his wavelength was 1.1 times the quantization of space, it would have these sort of lurches and jumps, and it would arrive, slightly out of speed. So one of the things that astronomers have looked for are energetic photons coming from some event where there's more than one, and to see is that shock front such that these energetic photons arrive ahead or behind the main blast of photons, and so far we haven't found that. But there's certainly is enough room for experimental error that they haven't confirmed it. It would be nice, but it would be nice to see, is the universe continuous or is it discrete? That's
I think right now they're definitely in the process of doing experimentation to find out the granularity. And I am a firm believer of the holographic principle. I really do think that is a very valid principle. I've been asked to try to get the live feed into the chat. I tried that. I had a problem with it. I'm going to try again, but please let me know if the feed starts doing that same thing he's talking about, the little perturbation and kind of like jerky, because because I've been having issues with the encoding software. It's not my computer, it's not the internet, it's the encoding software. And I played around with it substantially today, and I tested it, and it seemed to work pretty well. So I don't want to really do too much things to mess it up, but I will try to figure out if I can get the live feed, because live feed is booming right now. And I know in the outside chat if it works. Okay, so while you guys are talking,
one of
doing
that. I know that while you're doing. Go ahead.
I need to leave soon, so I have two questions.
Right.
One is regard to the Planck epoch, to have made some progress in describing what happened in the Planck epoch, and also, is the universe infinite? Or do you, if you go in one direction for infinite distance, will you eventually come back to the same spot, or will you go on forever, for example? And that's the two questions.
Really, really great questions about that. Is the universe infinite in terms of you? If you head off, you continue to go forever and ever, or is somehow the topology closed and you start looping around? And so far the observational evidence does not show the universe wrapping around. We don't see, for example, the cosmic background having sort of analogs where the stuff on this side starts mirroring the stuff on that side. That isn't to say that proves or disproves. It just means that at the scale of the observable universe, the universe appears not to wrap around.
I'm talking about the scale beyond that, beyond the observable universe.
Yes, and that's a bit hard. We don't know because we haven't observed it. So both you have to say that both haven't been ruled out. In that thing, in terms of the early era after the Big Bang and the Planck epoch, work going on at places like CERN trying to create high energy density, high temperature balls of energy to see how stuff interacts, while not anywhere close to the temperatures of Planck era, are giving us more insights into how, for sort of extreme physics, and what the early universe might have been like, a trillionth of a second after the Big Bang. And that's right now the best chance that we have to sort of give us hints as to what goes on. But we still have this big mystery about, was inflation, is inflation real? One of the problems that you have with the Big Bang, the classic Big Bang, was that the universe was initially very homogeneous, right? That light could equalize things, and that the universe was essentially a if you think of it, you can think of it as a compact mass that stabilizes, everything was equalized. But obviously now the universe is lumpy, right? There's chunks of stuff, things separated out, and chunks of the universe no longer can communicate with each other. How did we go from something uniform to something lumpy? And the answer that theoretical physicists have given us is this period called inflation. We don't know why it switched on and why it switched off, even if it is actually real. There's attempts at the South Pole of a thing called the BICEP telescope to try and look for some experimental evidence to confirm inflation. And they've gotten close, although there's some factors they had to rule out. And the next generation of the instruments that are there are likely to provide us with answers relatively soon. The last time I was there, they had found the signal, and they were actually quite happy. I go to the South Pole not to work on cosmology, but I'm looking for meteorites, so small, rocks from outer space embedded in the ice. But while I'm down there, I like to go and check it on my folks doing things like the neutrino detectors and these other amazing telescopes at the pole. They're trying to answer these questions about what happened between the Planck time and
the Big Bang.
The Big Bang, the Big Bang flash.
Yeah. And the Planck epoch is very important in understanding the origins of the universe.
Yeah,
do we have some?
Absolutely.
Do we have some idea? On my last question, do we have some idea about even before the Planck time, or no idea at all? What happened even before the Planck time?
One of the things is what became before the Big Bang, and one of the common maybe we common misconceptions, the Big Bang, time was created. One of the models that time is created in the Big Bang, so there isn't a before. Another model says there's more than one Big Bang. There's a multiverse, and you could ask questions about other universes, other universi, I guess you'd say, that have their own processes, presumably Big Bangs.
Yeah, and isn't it so that people are asking, why do we invest so much money in CERN? Why do we invest money in high energy physics? And two reasons, obviously. High energy physics get us closer to that Planck scale, right? It gets us higher to those pressures and temperatures that were originally existing to see what the physics were like. And the other thing is, we're dealing with wavelengths so short, so small, when in high energy, that you're getting to that granularity. So we're actually seeing the actual workings of the universe. We're seeing if, like you said, we look at the universe and we see some kind of contiguous form. We see something that's, like you said, homogeneous, although it's really not because of answer entropies. But we can't tell that there's been discontinuities from one.
Yeah, because the space appears to be continuous.
Right, exactly.
Right, time
so
appears to be continuous.
Can resolve that, though, right? I mean, that's why they want the high energy to get to those higher frequencies, means smaller resolution, so we can actually see the fine structure of the universe, literally the fine structure.
The other thing that may answer that question is astronomy, in terms of events that generate enormous energies of photons that we can then detect. And so some of the most violent events in the universe generate these very, very high energy photons that could give us insight into whether or not the space is granular. And that would really be coming back to the fundamental nature of space and time to begin with. If you're going to start wanting to play with very science fiction concepts of space-time travel, you better understand the physics of space-time travel much better than we do now in order to be able to rule out or figure out how to do something.
Is that more of a limitation of our technology or our knowledge that we have? We're making experiments to detect that granular nature of space-time. But do you think it's more just we haven't really refined the technology to get to that point yet?
I'm a person who was taught to be very reluctant to say, "Oh, it's impossible," right? That's a really bad thing to do. In fact, I don't think it's a very scientific thing to say. So when someone says, "Can people go faster than the speed of light?" my answer is, we don't know how, and I don't understand the physics that would allow that. I'm not saying it's impossible. It's just that the physics I understand does not permit that to occur. But the physics I understand could be wrong.
Yeah, but we
can also find. We can also find another way around it, like wormholes, for example.
That's not going faster than the speed of light. That's kind of just a loophole.
Yeah.
But you could always say, according to the theory, according to special relativity, you can't go faster than the speed of light. And that way, that would be impossible. According to special relativity, it is impossible. So if you frame the statement in reference to what you're referring to, then I have no problem with that. I agree with you. I don't like using the term impossible. Generally ubiquitously across the board saying, "Oh, this is impossible." But in the framework of something, according to special relativity, it is impossible.
Yeah, and it's sort of, so when someone comes to me and says, "Well, aliens travel across time and visit us and go back there," one of my responses is, I don't understand the physics that would allow that to occur, rather than say, "Well, that's bunk because blah 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 blah."
Well, the math would be interesting to see that, right?
Exactly, and so I always did one of my college courses where the thing was really about caveats, and say, when if you say something like things with temperature emit radiation. Give all the caveats, all disclaimers, and all of the nuances, and that'd be the test. You basically spend several pages giving all the particular gotchas and counterexamples of the things to understand that when you make these dangerous statements like there are no blah 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 or this is true da da da, you're on not on firm ground.
Mm-hmm.
You're much better off saying what you know or the limitation of what you know. That's actually, I think, more scientific.
One final
more
question.
Honest.
One final question. When you go back towards the Planck time, the four fundamental forces become unified, right?
Yes.
So
yes.
that
appears because
yes.
we see the process of unification. We certainly see the process of unification with electromagnetic and strong and weak.
Yes.
Gravity is
does it happen in when a star goes supernova, and how does it exactly happen if it happens?
I'm trying to think. The energies in a supernova, while tremendous, don't have the densities that are there unless now let me think about this. Unless, for example, one of the things you're talking about is like a type 2 supernovae where you're forming a black hole. And the process of forming a black hole is not fully understood. We understand a lot of it, but not fully. And there's probably some weird physics going on there. The both quantum mechanics and relativity theories start to get uncomfortable around things like an event horizon or forming of event horizons. So forming of black holes. Similar thing of merging of black holes is very, very weird. Of how they appear to merge. We have experimental evidence from things like LIGO that they do, but the physics behind those mergers is the description of those mathematical description of physics is still eluding us to some extent. We have pretty good ideas, but not fully. So it's possible that when you're forming the black hole, that there's some weird things are happening.
So for example, that some forces are unified in the process.
Mm-hmm. Oh. Yes, and so I'm thinking in energies there may be sort of extreme physics going on near the around the formation of a black hole. Would probably, but most of the stuff of a black hole is atomic physics that can be relatively described. Now, this isn't to say that isn't an amazing event. Supernovae are extraordinary bursts of energy that do extraordinary things, such as make the stuff that makes us, or most of us. So I don't mean to make light of them, but the kind of energies that we talk about in places like even like CERN, the multi-trillion degree stuff. Most of the supernovae is not dealing with those kind of extreme energies, but there are probably some very odd things happen with them, like the magnetic fields. If you've got a star that's collapsing, let's talk about the massive star. That's the type 2 supernovae where the massive star collapses, and the magnetic field that star has undergoes some pretty spectacular things. And some of the particles that can get accelerated out of those events, come flying out at extraordinary energies, and those energies cause them to collide and do really extraordinary things. So yes, I'm not ruling out that there could be events there, but the majority of the supernovae is at temperatures that are a little bit saner than where physics is.
You really have to have the
sane.
Planck scale type energy levels to have the everything to be unified.
Yes.
I mean, it's mind-bogglingly hot. We couldn't even imagine those kind of pressures and temperatures.
The first force to be unified is the electroweak force.
Well, it's electromagnetic and then electroweak.
Magnetic, yes, and also I have to go now, and I want to thank you for your answers. I really enjoyed it.
I hope that some of them are plausibly
this is great.
believable. And
This is
I want to
awesome.
thank you. I want to thank you for excellent questions, because again, science is about
thank you.
questions, and you did it. Your questions were excellent.
Thank you.
Most people
And also
life here
very
are just
important. And
confused,
these
but
are
that's
people.
okay. No,
People are working on these things. When I say we don't know, I don't mean to leave it there. These are actually really important questions that people are working on. I hope we can find the answers to it, gain insight into it.
Yeah, great answers, great questions, certainly.
So, Landon, I'm given to understand that there was another search of the same kind, another search attempting to determine whether the universe was accelerating, sort of the same kind of search that Hubble did. And I am given to understand that the early results seem to imply that it might not be. Do you consider that a serious challenge to the idea of dark energy existing, or not really?
I asked some. I don't know which one you're referring to, but there was one of the results where someone came out and gave an alternative explanation. So I went to one of my colleagues, Dr. Filippico, is much more expert in this thing. I was part of the team, and he explained that the observation was missing some fundamental items, and that he didn't consider the questions they were asking were not well formed, and the results they were claiming were not credible. There are 4 different now independent processes that measure 4 different methods for measuring dark energy. So it seems and pretty sound that there is something out there. I mean, most of the universe is this dark energy. Question about what it is in a much more active ground to try to understand. But the fact that so there are people come up with alternative explanations, and again, I'm not saying they're crackpots. They're serious scientists who are trying to challenge things, because they're asking questions. But so far, no one has come up with something credible that would say, dark energy doesn't exist and the universe is simpler.
Awesome. You mentioned the Casimir effect earlier and how it was far too weak. Our observations of it were far too weak. Are there any hints that the Casimir effect might, I don't know, be proportional to the amount of matter nearby? Could the Casimir effect, for instance, plausibly be much stronger in interstellar space?
It's possible. One of the things that you see with the effect is that we don't, for example, we haven't seen dark energy being asymmetric. So when we look towards massive lumps, we don't see necessarily that there's more dark energy that way than that way. We don't see the supernovae inside dense galactic clusters being in a different expected distance than the ones that are in relatively isolated regions. So that's an example that suggests that it doesn't seem like dark energy is clumping. Now, a very active field right now is to verify that and try to measure the amount of dark energy in various directions to see, does it, is it uniformly distributed across the universe, or is it lump, as a clump, as you say. And so people are designing experiments to try and measure and determine that to be the case. Right now, the best method that we use is either looking at these events called supernovae, type 1a supernovae, these things that have sort of a typical energy level, and you see how bright it appears to be able to measure its distance and to get an idea about the universe and how it expanded. The other, another method is to look at the echo of the Big Bang, the cosmic background radiation, and look for imprints on that echo that would imply a structure of the universe. It's another method that is where we can see evidence of dark energy, and perhaps to comb through that, to look around to see, is there like more dark energy that way than that way, as an example.
We've always assumed there was some kind of homogeneity to the universe, but I mean, is there anything in science that says that in the early formation. I mean, just like during right after the inflation period or right after recombination, that there had to be something that was homogeneous throughout the universe, that there couldn't be something that was tipping the scale one way or another, like the fine structure constant would vary from here to there or something, or some kind of symmetry violation where you'd have more production of this and less of that, something that tipped the scale to create the universe as it is now, whether it be the fact we have more matter than antimatter, or the fact that we see these large scale things in the universe that shouldn't, according to what we had been brought up, I'm sure it wouldn't normally have existed, these large scale anisotropes.
Well, but so you actually said a lot of very important things there. So I'm trying to figure out where
I've only got you in it for a little while, so I'm just hitting you.
To begin. So
I'd love to get you and Hugh Ross
things,
together. That would be amazing.
One of the things that is so the typical models that are employed in Big Bangs talk about the fact that pre-inflation the universe was homogeneous, and post-inflation the universe accelerated at this exponential growth and resulted in the universe being large enough that light couldn't get across, can't go across the other end, and everything's equalized and stabilized. If you can get light and other forces to move across the universe and back and forth, then if this were to get hotter, it would radiate and cool down, and the other part would pick it up. But if your universe is too far apart, so photons can't reach across because there's not enough
The horizon problem.
time for the photons to reach, then things can become asymmetric, and you get asymmetries and you get lumpiness. And so the inflation models are typically was put in there to attempt to explain how the universe started off at what would be seen as a uniform, high density, state, and turned lumpy. And so people are looking for evidence that the inflation is a nice mathematical hack. The question is it real? And so people are looking for evidence of inflation. And one of the evidence in particular is that the universe at about 387,000 years after the Big Bang appears to have gone from translucent to transparent. At that time in the universe, a very important thing happened. Prior to that, you had free electrons and protons flying around this plasma, and photons were any photon was generated would travel short distance, be reabsorbed, and basically had this sort of generalized glow. But as the universe expanded and cooled, hydrogen formed. These protons were able to grab onto an electron and form a hydrogen atom. Neutral hydrogen formed, and at that time, the universe had this giant flash. All those photons are bouncing in around into the plasma. All of a sudden, you just had neutral hydrogen, and they took off, right? And those photons are the microwave background we see today. We know that because the stuff has been redshifted. It started off on the hydrogen, the hydrogen emission lines when the event occurred, but it's so far redshifted, it's way down in the microwave at this point.
Yeah, and it should be noted that was predicted too, right? I mean, in order for that Big Bang model to be correct, the opacity of the universe had to go away at some point, and the photons are all bouncing around because of a high degree of electrons. Finally, were able to escape, and that flash, that CMB, the remnant, was predicted, and it was literally predicted to be the temperature is at 2.725 Kelvin or whatever it is. Yep. That's what's predicted, and that's something that is very strong in what science, as good scientific models should do.
And the black body, the black body curve that generates is just classic there. Now, the other thing that was predicted was there were fluctuations, because you could not have had the universe cooling down instantaneously everywhere at the same time. And quantum mechanics would say, no, you can't do that anyway. But the sound waves that were going on inside that plasma are imprinted on this flash. Why? Because there were areas where the sound waves were compressing, where it had slightly higher temperature, and so it took it longer for it to go transparent than places where the sound waves were expanding stuff. It was cooler. So there's temperature, we call it temperature fluctuations, but the other way to think about it is that the universe went transparent not at an instant in time, but over a short period of time, and the lumps took longer than the rare forms. Those show you the structure where matter is. It shows you where the energy was slightly variation. And so when you look at the maps of the cosmic background from something like WMAP or COBE, you see very tiny fluctuations. And we're talking about, fluctuations is a part of like small. 1 in a million to 100,000 of a degree. Very, very tiny fluctuations, but nevertheless,
the fact we can have
there's structure
sensitivity for
there.
that is amazing.
Yes, and that's the amazing thing. The experimentalists and instrumentationists have produced some amazing information that that is quite astounding. That's remarkable that they've achieved it. But one of the things that is important about those maps of the early part of the universe that we can see, is that the photons that bounced off of the plasma just before it went transparent should have inside it an imprint of much earlier times. And if inflation were occurring, there's certain polarization effects that should have been left, so that the last ricochet of the photons off of the plasma before it went transparent and we see the flash should tell us about the state of the plasma at that time. And that state of the plasma should have left over the repercussions of inflation. So telescopes like BICEP at the South Pole are trying to measure extraordinary precision the microwave background in order to see if you will, the twang of the last echo before the universe went transparent, in hopes that will give us data insight on inflation, and also perhaps some of the stuff regarding direct observations of gravitational waves, and on perhaps even if we were lucky, some kind of quantization or Planck quantization of the universe. So people are hoping that they're able to get results. The first results they presented suggested they might have found it, but it turned out that there are some effects they have to deal with in terms of dust between between us and the microwave background that they need to take into account. And in order to handle that dust, they have to increase the sensitivity of the instrument. Not that they got it wrong, but that the extraordinary results that they're trying to achieve require extraordinary evidence, and people are being extremely careful with this, and hopeful that the next generation of the detectors will give us some definitive data about some of the echoes that are going on inside that plasma pre-Big Bang flash.
And you admitted
it's exciting.
You said how careful they are in their calculations, and careful when they discover something. Just like you had mentioned, the gravity waves. They dotted their I's, they crossed their T's. They were validating that to make sure they had actually discovered what they discovered, with independent corroboration. correct? I mean, that was
the gravitational waves that were discovered by LIGO.
Mm-hmm.
By the way, gravity waves are a phenomenon you see in clouds, but the gravitational waves.
Yes.
By the just
you got me. Gravitational waves and gravity waves are two different things. Yes, gravity waves.
By the way,
I
did the same. I did the same thing in a lecture. So I
No,
the gravitational waves.
We love being pedantic around here. You got to remember, half the people that come into my thing here are like, PhDs of this, that, and this, and if somebody says something wrong, they're all over it. So we were fine with that.
And I apologize for any cringe basic statements that I've made so far. But if the gravitational waves that, for example, the LIGO detectors have, appear to be really solid data, and the fact that you have two detectors that showed now several events of what we model as black hole mergers is quite exciting. There is another generation of these gravity wave detectors coming online, gravitational waves, detectors coming online, and just getting the third detector out there will give us ability to have direction of where these waves go, to help it pin down more sensitive detectors, to be able to narrow down where in the sky the source is. because it'd be nice to go and point radio telescopes or optical telescopes or X-ray telescopes at the thing to say, is there something suggesting that there's a twang in space? Look there to see where the twang came from, to see if you can see any counterparts to it. Would be nice to.
Yeah, they're also thinking about putting it. Well, they want to put them in outer space too. These lasers.
Yeah, LISA is a very important project that I'm not sure. I mean, I was certainly promoting its funding back about a decade ago, and I hope it's a technological challenge, but I hope that it's one of those things that can be launched. LISA is going to give us sensitivity to a different part of the gravitational wave spectrum. We have spectrum of light, right, and from radio waves up to gamma rays. Well, gravitational waves are completely different, completely separate spectrum, and there are various frequencies. The type of frequencies of something like black hole mergers is a very different frequency space than something like a supernovae occurring. And so LISA is going to be going for a different part of the gravitational spectrum that is that's going to give us insight to different phenomenon than there's. So it's not merely just, it's not like a bigger telescope. It's a telescope that's sensitive to different wavelengths. It's like saying we've seen a couple of photons of light from a couple of events, and now we want to build a radio telescope. That's kind of what they're doing in the gravitational space to see
the verge of radio telescope only gravitational wise. Yeah.
Steve, we have a question from Albany. Can I just confirm, when dealing with these kinds of data, the analysis methodology are all agreed upon before any data is even seen by the analyzers?
Okay, so are they saying that that there's agreement on what the data is, how the data is processed? Is that?
Yeah, but I guess
what I was actually trying to get at is that when the scientists actually dealing with potentially groundbreaking new discoveries here, all the analysis, the techniques and the methodology, they're all completely agreed upon, they're all discussed, they're all agreed on, so that there is no potential contamination of conclusions that are eventually received because people might be wanting to use a different methodology or something. Everything is already set down in stone before even a single data point is seen by anybody.
I mean, that the current, I would phrase it differently, that the current methodologies are recorded in how it's done, and when it's published, the details of what was done and the certainties around it are published. And particularly when it becomes groundbreaking, what you're trying to do is say, we have observed this, and this leads us to this conclusion. Can someone else confirm? And so someone else can either try to reproduce your experiment based upon how you describe it to see if they get the same results. And other people can try to come up with different experiments to examine the same phenomenon and see if they can agree. But I wouldn't say that there's necessarily an agreement on how the data is going to be analyzed. That certainly an experiment has a methodology that they develop, and that's part of what they publish when they publish a result. So if someone comes up and says, we have observed this comet outgassing, they will then produce their data, produce the images, and discuss, allowing someone else with observation to look at the comet and verify or not. And they might publish something saying, well, we looked at the comet and we didn't find outgassing. So perhaps there was a problem with the detectors. Someone else goes and looks at it at a different wavelength and discovers that the comet is quiescent and suggests that maybe that one experiment was an error. Someone else might come and say, no, we have a much more sensitive detector, and look, we see the trail from the outgassing. That's sort of how that stuff goes forward. But you try to publish your data and your methods so that someone can reproduce, they'll choose, and other people can look at it in a different way to see if they can find a contradiction or not. So, and that sometimes happens where really valid data comes up with this, and then another method comes up with a different method, and then you try to reconcile the two processes.
You know, we have barely scratched the surface on all this stuff. I mean, you are so vastly educated on many different types of things. I mean, we could literally spend hours talking about a specific thing. I do like to keep these things down to about 2 hours. That way it's easily digestible to people. And we are going to bring you back. I mean, I'm going to hunt you down. And thank you, Red Eye, so much for bringing Landon to our community. And yes, he is.
Thank you, Red Eye. I enjoyed this conversation. It really is nice to have a nice conversation about science, how it works, and the excitement of stuff. I mean, that's the cool thing. This stuff is really exciting. And
we do have a few questions, though.
I'll get to it. I was going to drag. I was going to say before, I'm not ending it right now, but I wanted to end up with a few questions from the live chat.
Sure, please.
And but I wanted to note something very important, that when we have a guest like this, as compared to Mr. Intelligent Design, who's in the live feed for the last 2 hours, who by the way, Landon is familiar with. I want to show people the difference in quality of a person who does know what they're talking about, that has a background in these different topics, and to the panel that is obviously asking questions that have some kind of familiarity with these subjects. I mean, obviously Neslig and Chris and even myself to a degree, we've at least read books on this stuff. We've actually familiarized ourselves with these topics, and then you see somebody able to answer questions in detail and expressively so, and not get overblown with jargon, but to the point where it's, oh, hey, you know what? I can explain this the way anybody can understand it. That's the difference.
Notice also the number of times I said I don't know, or we're trying to work on it, right? I didn't give you answers. I suspect I gave you more questions than I did answers, which should be how science works, right? Someone who says, this is truth, here's dogma, read my book, everything is, answers are there.
Accept
scientific. And Red Eye, please do your book review. That'll be a fun thing.
I think he kind of gave up on that. I don't know. I'm asking I mean, I don't know if he even made it through the entire book. And again, I hate to call it a book because it's not really books, but whatever. So anyways, from the live feed, what questions we have from them?
There's one about flat Earth. I'm not sure if that was sarcasm or not, but
well, as someone who has actually stood on the South Pole, when we do an expedition of looking for meteorites, one of my jobs is to find the South Pole so I can put my finger. I mean, find it within about a centimeter of stuff. And then, of course, one of the other fun things I do is once I find the South Pole, I conduct an experiment. Does gravity work upside down? And I jump as hard as I can off the bottom of the world and see, and every time I've fallen back. So far,
that's just an Illuminati
gravity works.
We do have a question from Tom. Maybe Steve can ask him about rival theories like the one proposed by Roger Penrose, and what his opinion is about the CCC, or conformal cyclic cosmology.
I attended Penrose's lecture with Dr. Filipinko on that, and I have to say the result of the lecture was kind of tragic. That there was some fundamental things that he didn't address in his theory that was kind of tragic, and it was really, there are a lot of cringe statements he made that aren't really supported well scientifically, and it's not, unfortunately, not well regarded. And I came there with open mind, hoping to hear something from a great person who's done great work in the past, but it ended up not. I was not satisfied that there was much to his. Because there was a phenomenon that he wasn't addressing.
Do you think Penrose kind of fell into woo-woo? I mean, you're familiar with the orchestrated objective reduction, like this consciousness that forms from quantum fluctuations in these microtubules, and it's a fascinating stuff. And I mean, I grew up reading Penrose. I grew up reading Davies and Asimov, and I mean all these guys. And it seems like he kind of later on kind of just got in more in the woo-woo aspect of quantum mechanics than some of the other people.
Yeah, but it certainly quantum mechanics attracts that sort of thing. But the
would you say that's true then? He kind of did.
I remember my colleague turned to me and said, when I get to be that old, if I start saying stuff like that, pull me aside and tell me that I need to do. And that was I want to be kind to him, because again he's done great work, but it was done in a public lecture where you don't stand up and say, you forgot the blah, 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 because then you look like a jerk, right? Mm-hmm. So I spent a lot of time cringing when he made statements that were not, backed up or ran counter to the evidence.
Kind of like what happened to Crick.
It was kind of
wasn't it Crick from Watson and Crick that kind of went off the deep end?
Yeah. On there. So, but sorry, again, great respect for the work he's done. That lecture was not one of those pieces of work, but I've done things that have turned out to be stupid. So,
Okay,
it happens to the best of us.
I think actually Andreas had a question. Would you say the presence of transcendental numbers is key for us to better understand the universe, and does it provide us new ways to formulate functions that describe these phenomena?
I mean, they're talking about these numbers that are not the result of finite. You can't take some polynomial and get the value. So things like pi are a deep part of mathematics. There's your earlier question about, is the universe digital, discrete, or is it continuous? If the universe is continuous, then these transcendental numbers do actually apply to the structure of the universe. If the universe is a grid, then you don't have a perfect circle. You have these sort of wobbly polygons that are going to be mostly in the rationals. So it's an interesting question.
Is that the current thinking though? The second of the two?
That is one of the thinkings of that. I don't purport to be an expert in that debate, other than the fact to say that the experimental evidence is not there to show that it's either definitively continuous or it's discrete. Mm-hmm. The observations of very high energy photons coming from very violent events in the universe have not found solid evidence of a discrete quantum length. It's possible that the signals don't give us the kind of information we think they're giving us. It's also possible that the granularity is not having the effect on the photons we think it is. I mean, just because if the universe was granular and you had photons that were in some non-uniform wavelength, it's possible there's some physical mechanism that we don't understand to give us photons still arriving at the speed of light. I mean, the universe seems to be dead set on this. Photons go at the speed of light.
Yeah.
All the time, no matter what.
It doesn't like variation in that.
And there could be some weird interactions of relativity down in the quantum level that we don't know, where photons continue to go at the speed of light. The universe seems to be pretty stuck on this C thing.
Yeah, the variable speed of light model was not looked upon favorably to solve the horizon problem. Okay, what do we got next?
Yeah.
The next question.
Actually, how about Red
Eye? That was a great question, by the way.
Does Red Eye have a question? Because Red Eye actually made this happen, so at least he can do is ask a question. And I even allow Mr. Intelligent Design to ask a question if you guys don't ban him on the live feed.
I didn't do anything to him.
I timed him out.
Yeah, Red Eye. By the way, Red Eye does ask really great questions.
Smart dude.
And the other thing it's nice about explaining to Red Eye is that he gets so excited about really amazing stuff. It's quite a pleasure to introduce him to concepts of black holes. And
one comment is that someone wants to see your entire T-shirt. They can only see the top half.
We could have a whole hangout on black holes.
It says dark energy is the new black. That's the T-shirt that the discoverers of dark energy gave to themselves. They gave one to King of Sweden and one to me. So.
That's awesome.
All right. Speaking of dark matter, there's another question. I think it was RSC. What does he think about dark matter / energy just being a yet to be observed property of gravity on large scales?
There are people asking questions of, could the reason why we can't find dark matter particles be because gravity is different on large scales? And so when you say that, then the next thing you say is, and therefore, I predict when you look at this phenomenon, you should see this instead of that, right? You didn't try to make a statement which is falsifiable. And that's something, for example, that some of the people pushing books and dogma don't understand. The next thing you do is you say, my my theory includes the ability to be falsifiable, to be able to prove it wrong. And here's how you can prove it wrong. So you go about developing what's called the null hypothesis. The null hypothesis saying, which is the counter to that, and you go about trying to disprove your theory. And that's one thing that the people that peddle these kind of quack stuff fail to realize, is they're trying to show how they're right, how the world is flat, and prove it. That's not how you do it. You try to disprove it, and you fail to disprove this is a scientific method.
Yeah, sounds good to me. Here's another question. Oh, that's about C. Brown. Regarding dark matter, are you convinced?
No, oh, dude, you can't just pass that up.
Come on, okay. You want me to?
I would love. Oh, yeah, come on, just go.
Come on.
Yeah,
okay,
come on,
okay.
seriously. Okay.
So we interact with a gentleman by the name of C. Brown. This guy is so I think the word is duplicitous. I think that's the word that Steve uses to describe him. I jokingly placed 2 of my genetics homework problems on Google Plus for him to solve, and he ran straight to Google, like word for word, copy and pasted it. That's kind of the level of I guess
he tried to pass it off as
caliber.
Don't forget that he tried to pass it off.
He tried.
He sunk as low as going to Yahoo Answers.
Yeah.
I by the way, I have to say that Mr. Crust, who talked about G-Man would say, so you have faith in gravity. No, I don't have faith in gravity.
Amen.
Gravity exists whether I believe it or not.
Amen.
That is true.
Absolutely.
That is true.
Sorry.
One of the things that C. Brown said was the funniest thing that I think we've heard in ages. And I'm going to literally say it to you the way he was saying it. Hopefully it got it pretty much correct. And then you give me how you would respond to it. He claims that all elements were formed due to what's called Z-pinch, which is we do know exists. I mean, that's Z-pinch is how they work in tokamak reactions or fusion reactions. Now he's claiming though the Z-pinch of lightning created elements like uranium and all these things have decayed into what we have now. So lightning is the cause of all the heavier elements on the planet. How do you respond to something like that?
Well, a couple of problems with that. When you observe lightning, we don't observe element production in the cloud. In fact, one of the things I was involved in an experiment relating to actually lightning storms over New Orleans. Their New Orleans area has fantastic lightning storms.
Yes,
and
it does.
There are these things called amazing stuff, and there's things called reverse lightning, where essentially you get extra charge in the ground and get this reverse thing coming back out. And we had things like the Chandra X-ray telescope and other instruments in space looking at the result of the X-ray production of what happens when they have these really extreme lightning events occur. Why were we interested in that? Because we wanted to understand what lightning looked like from space in various parts of the spectrum. Why? Because when we're looking at extrasolar planets, stuff way out there, and we see emissions, we want to be able to say that's emissions from these, really extreme lightning events. This is what it looks like close to Earth. Let's look at it in space and see if we see something similar. And anyway, in that process of those really energetic storms, and I had the pleasure of being in New Orleans when this storm occurred. It was really quite an amazing show. But from outer space, we would have seen, gamma emissions if they were like nuclear processes going. We saw X-rays, right? Because you get superheated gas, you get electron transitions that are quite extreme. But we did not see the gamma rays that would be associated with high energies showing, element transpositions.
Wondering to ask exactly what kind of conditions are required in order to synthesize stuff like uranium, thorium, those really excessively heavy elements.
It appears you have to have high density, high energy collisions of particles of nuclei. And in fact, the kind of stars which begin to fuse iron appear to be really good at generating the uranium elements and some of the transuranic elements that decay rapidly back down to uranium. But you need time, short periods of time, a very high density, a very high pressure, very high temperature in order to fuse things like that. In heavy ion accelerators, we typically do things like lead and bismuth to create elements like 117, 116, 115, those sorts of things when you have these large collisions. And you typically pick something like lead because it's a fairly dense material and it's fairly easy to get in pure form. It also has and it's harder to just slam uranium atoms together and get anything other than just this shower of stuff. It's really easy to smash atoms together and have them go blam across there. It requires a lot of pressure and temperature to get them to fuse and stick there. The kind of things that appear to happen inside supernovae.
Hundreds of millions of degrees.
Yeah, it's quite extensive. I mean, like you said, fission's easy. I mean, that was my background. I was a reactor operator, as you guys know. So, I mean, I learned a lot about fission. Fusion, whole different ball game. Oh my goodness.
So yes, I love. I had fun memories of working at the Reed reactor in
I was going to ask you. You had actually worked at was it Lawrence Livermore? Did you work at?
Yes, as well.
Yeah.
But the Reed reactor is cooler because it was one of the reactors in a pool. You can see they actually shrink off radiation.
You see Chenyakov radiation?
The real good stuff. The glow, the nice glow in the dark.
Glow, the Chenyakov radiation.
Oh yes,
awesome.
It's dead obvious.
I only study pressurized water reactors. Very specific. Type.
See there,
I know. I know. I'm simple. What do you want?
And we were,
but I did qualify
when
yeah.
Yeah, but say when Mount St. Helens was erupting, right? The reason why we were there to the south west of the mountain and blew up is we were grabbing samples of ashfall, flying back, coming as rapidly back to Reed as we can, put them inside the reactor to neutron, cook them with neutrons, and see the gamma rays that are coming off, and to be able to understand the elements. We want to know the elements. What was the element mix that St. Helens was doing? Because we knew we had this magma event, and so we had deep material stuff being exposed. So we wanted to get that material in and understand the element mix as fast as possible. And so, and while you're in there, cooking, some of the times I didn't go back up to the mountain. I basically sat in a chair by the poolside and we could read from the glow of the reactor. It was actually
that'd be scary, but yeah. I mean,
I have to. By the way, I have to admit there was a lot of excitement because we wanted to get the material into the reactor, particularly to see what kind of radioactive material might be coming out of the volcano, and other short-lived events to see what's happening. Because one of the things that was happening was there was a lot of lightning events that were occurring. The volcanoes generate a lot of static electricity when you're having outgassing from magma. So you had lightning arcing from the side of the mountain up into the cloud, and giving us some additional mixing of stuff. They wanted to see what that was doing, chemical wise, as well. And I have to admit, I did something slightly naughty. I snuck in some uranium-238.
Yellow cake.
Cooked it. Yeah, my excuse was this was a test sample. I didn't have a reference sample, and cooked it to some plutonium, which is still sitting in the reactor. Obviously.
Yeah, that's well, U-238, not a big deal. Plutonium, not a good stuff.
So I did it before Kim Jong-il did.
Yeah, you create. Was it weapons grade?
No, it was enough that I could detect gammas to say, yeah, there was some plutonium.
I wouldn't mess with
and some americium.
That stuff is just too dangerous for me. I would eat.
I mean, we're talking about, again, these are vials you put samples into, and you put it into a gamma ray spectrometer to be able to determine the elements. So what I'm talking about is a handful of atoms was created.
You remind me of somebody who'd have like the demon core and go, "Oh, this is cool."
As a kid, I had an element collection.
What's that?
I had an element collection, and so I claimed that for some period of time I have plutonium, and americium in my element collection, but And so they're still in the reactor pool because
Tom says nobody gets my joke. Oh, what do you want? Okay, 3 people understand my joke.
But I liked it. I liked your joke. I liked your joke. But anyway, yes. So I have fond of reactors, particularly the ones you can see.
No.
Yeah, luckily, like I said, the reactors I worked on were much more. I'm not going to use a safer, but I mean more confined. I mean, pressurized water reactors are inherently safe.
What other question we have from the audience?
Someone asked earlier, could you ask what his opinion, what is his opinion on being able to escape from a black hole? That's interesting. How do you avoid spaghettification?
Oh no, it was about information. Sorry, the question that was asked was about information.
Does information get destroyed in a black hole?
I skipped over that word completely.
Encyclopedia bet.
Yeah, exactly.
I'm not sure that, and in fact, when it was interesting when Hawk and I discussed his bet, I was surprised at how little he was willing he was to give up his bet, because I don't think it has been answered fully. But for some reason,
with the firewall paradox, or the firewall that Susskind actually kind of resolved it for Hawken.
In that sense, but one of the things for certainly we haven't been able to experimentally verify that. I don't know how you would do that, but that's one of the things.
But Hawking did admit that. I mean, he gave it up, right? I mean, he actually said that information is conserved, right?
I mean, that's what he seems to say. But I, given how much trouble both quantum mechanics and relativity has around event horizons, it seems to be a little bit of a stretch to use those to come back and say, and therefore it's conserved, right? The quantum mechanics says it's got to be conserved. Relativity says, well, maybe not. The one of the things that I would like to see is confirming that Hawking radiation actually exists. I hope it does. It would be a nice result, but we've yet to be able to show by observation that a black hole is leaking.
Doesn't, and if they create a micro black hole in like CERN, they're big trouble.
I mean, that's why I'm hoping they're able to do something like that.
Imagine, we hope this exists, but if it doesn't, we're all dead. Great.
But then some of these other violent events that go on in the universe of neutron star mergers and other things would have generated these micro black holes, would have solved everything anyway. So I think it's fairly safe to try to generate, if it's possible, generate micro black holes, particularly because if they exist, they surely would have played a really fundamental role in the nature of that early space, right? Going on. That if the Big Bang created a whole flock of black hole sizes, small and large, those probably had a really fundamental impact on the nature of space-time. So having direct, experimental evidence that Hawking radiation does exist would be a result that's really, really nice to achieve, if that's possible.
What else you got for us in the live feed?
Oh, sorry. Chris actually in the side chat.
Here, Drag.
Well, I was muted. Oh. Sorry. Chris in the side chat was asking about, are you convinced machos are disconfirmed as an important contributor, and are wimps the only other game in town?
So the question, I'm probably referring to the constituents of dark energy, excuse me, dark matter, and what could make up dark matter. I mean, one of the things at one time people tried to explain this missing mass was, well, maybe there's non-glowing, compact objects out there that aren't stars, but just lumps of matter, and there's a lot of it. And obviously, since it isn't fusing, we can't see it. And we don't see real strong evidence of compact objects like that. Why? well, when we stare out, we don't see, for example, if a compact object comes in front of a distant galaxy, if it came in front of in line, then for a period of time, gravity would be lensed, and we'd be able to see these sort of Einsteinian rings pop in and out. We don't really see that to the degree, these sort of transient events that we'd like to see. We also don't see when things like the bullet cluster observation came forward, where what happened is these two clusters of galaxies passed through each other and stripped each other of the material that was not really bound up inside the galaxies. Most of the material you can see glowing in X-rays. We didn't see enough of that to say, oh yes, there's all the machos, there's all the compact objects there. That's the missing mass. I mean, it was the ratios we saw was about 1 part glowing stuff in stars to 4 parts stuff that we understand to 24 parts gravitational mass that's somewhere, and it's the dark matter. Supersymmetric particles and these other sort of weakly interacting particles are sort of your typical particle physicist guess as to what dark matter might be like. Why? Because you got to have something that's got mass, but it's not interacting with matter. So you say, well, reason why we can't see it and touch it and see really obvious evidence of it is that, like neutrinos, it just kind of passes through. And they're saying that these dark, the Pentel explanation is these dark matter particles are even less weakly interacting than neutrinos. And the reason why we haven't detected them is that they're so weak in the interaction that we haven't had a sense enough or spent a lot of time looking. But with things like the Xenon 100 experiment, these chambers isolated deep down in the Earth, isolated from radiation from space, we just haven't seen the type of evidence of these dark matter particles interacting yet.
I'm sorry.
Okay, so I guess the answer to this question is, it seems like the compact objects are falling into disfavor because observational evidence, it's harder and harder to believe that, and the particle physicists have yet to produce the symmetric particles to say, yeah, here's your dark matter. See, we created it in CERN. Maybe because we don't have the energies, or maybe because it doesn't exist. It's hard to say.
I have a related question from our friend Odian, who messaged me. He asked if the universe is expanding nonstop forever and ever, which we don't know if it is or isn't, but and dark energy was causing the universe to expand. Does that mean there's an infinite amount of dark energy?
Well, certainly for the observable universe, there's not. There's a finite amount. If the universe is infinite in scale, then and dark energy is part of a property of space, then there would be an infinite amount of energy. But if you have an infinite universe, you have an infinite amount of stuff anyway. So
it'd be infinite amount of dark matter and normal matter, and dark energy and normal energy. And
yeah, okay. But for the observable universe, no, it's purely finite. And one of the interesting and this is something I did with Susskind. One of the interesting consequences of dark energy in accelerating universe is that that you only have a finite amount of time to interact with matter. There are objects in the observable universe for which we can never interact with again. Why? If you sent a photon, let's presume relativity is correct. You cannot transmit information faster than the speed of light. There are objects, 12 billion light years away or so, that if we send a signal towards them, it would never reach it, because in the 12 billion years it took for that signal to reach them, more space would be added, and it would never catch up. Right. So what it means is that if you are this omniscient thing that can go and grab energy and shape it to what you want to do, there's only a finite amount of stuff you can get hold of before the rest of the universe accelerates away. That has implications on computation, because what I asked was, if you could command as much matter as you can and build this computer, and let's say we bring the computer down to almost a black hole, because if you make a black hole, then you have I/O problems with the computer. Sans the question about the encyclopedia bet, but if your computer is brought down to almost a black hole, so that why? Because you want the signals to move across the computer as fast as possible, and let's say you make it a quantum computer, and you let this thing run for all time. One of the problems, you're only able to grab a finite amount of mass, and then with Hawking radiation, that thing's going to decay if it formed a black hole, and if not, the protons are going to decay down. So you only have a finite amount of time to use that computer. So what does this mean? It means that if our understanding of physics is correct, there's a limit to what the universe can do to compute. It can only do so many calculations before you run out of stuff. If you have infinite amount of time, you're an omniscient being, you only have so much computing you can do, and there are things that are not actually computable. It's an interesting result for if the physics is correct of putting limitations on omniscience.
People in the live feed are telling me my mic is low. I don't know why. I haven't done anything different. I don't think it started off low, but I will. I just checked my settings and I boosted it up a little bit. Let me know if this makes a difference. But I guess Mr. Intelligent Design does want to ask a question, but I don't think he's having a proper way of phrasing it. Drag, could you kind of parse out?
I'm trying my hardest.
I know
figure out what he's
difficult.
asking.
But I would like him to have his opportunity to ask Landon a question here.
I'll ask, and I mean, if you understand it, Mr. Noll, you are better than me. Okay. Since where will the universe place its particles if it has no space? I mean, which originates space?
Since when? Sorry, repeat that again. Let's see if I can parse that.
I think I understand it. I think I understand his question.
Just what he's asking.
I think he's asking where space comes from. What causes space?
Yes, what causes space to be propagated, in essence.
Okay, so because he makes a distinction in his first question from space and universe. It was my understanding that the universe includes space.
I mean, what causes space? Or why do we have space? I'm thinking there's these several. If that's what's being asked, there might be a couple of ways to approach it. What cosmologists would say that space was created in the Big Bang event. It's a property of our universe, and it's a property of the Big Bang interaction. It's interesting in that, for example, one of the things that people ask about the Big Bang was, didn't the Big Bang violate the conservation of energy? How did you get something out of nothing?
Great question.
Wasn't there something before? And how did you get space out of nothing? Right. And part of the answer is that, well, you can. In fact, one of the things that would happen if you were to take all the energy and sum it back up, is you get a big fat zero.
So the total net energy of the universe is zero.
Yes.
Mm-hmm.
Now, why is it? What do you mean zero? Right? Because I have energy. I do think. I shout. I do. And the answer is, well, there's about things like I guess the way to see is about there's potential energy and kinetic energy. That when I lift this phone up and if I were to drop it, right, and the kinetic energy, I haven't created energy. There's basically negative energy comes back positive energy. And the same sort of thing. The Big Bang process, one of the fundamental physics parts of the Big Bang process, has to generate universe. It generates space and time without violating the laws of conservation of energy. There's nothing before and there's nothing after. It's just a different form of nothing. It's like saying you have 0 and you pull out +3 and -3.
Yeah, the total amount is 0.
By the way, understand these are analogies, and if you don't have the mathematics behind it, it's hard to show you in the equations of how that happens. But what I'm giving you is the best analogy possible. So where did space come from? It came from the Big Bang.
And do you want to address real quick the other thing they bring up is the second law of thermodynamics, which is probably one of the most misunderstood things of all time in thermodynamics. I mean, I've yet to have certain people in our community fully understand, even remotely, the second law of thermodynamics. They really have this bastardization of it.
Well, it's easy. It makes evolution impossible.
Yeah,
That's what the
according to them,
second law of
evolution's impossible.
thermodynamics
Clearly.
is.
Yeah, clearly. Yeah.
I mean, that's not what
So why
I
doesn't
learned.
the creation of the universe violate the second law of thermodynamics?
When what you get, or we think you get again, this is in the inflation model. If the inflation model is reasonably correct, during that, let's say that Planck time, pre-inflation, is that you have a uniform density of energy. It's still zero, but you've got positive, negative energy in that set. So you haven't, and it's uniform, but you then begin to get complexity because quantum structure starts. You start getting quantum fluctuations. Now on top of that, you have inflation, and it's not really fully understood as to where inflation came from, when it started, and when it stopped. But the best inflation models then say that you had quantum fluctuations, sound fluctuations imprinted on the universe. The universe then went through this hyper expansion, and the result is the universe is no longer able to equalize and stabilize, and you began to see structure from the quantum fluctuations that occurred just before and during a period of inflation. Now, there's other cosmologists that explain this much better, but that's sort of the best way that I would give you sort of lay person.
It's excellent. And it's funny, is Mr. Intelligent Design is literally in the live feed, obviously not paying attention to your answers, because he's asking, he says no mechanisms to check. Well, no, the quantum fluctuations, which are an inherent property of reality because of Heisenberg's uncertainty principle, those are the mechanisms of why these things occur. Matter of fact, there's a paper out there that shows mathematically, because of these mathematical facts that we cannot have specific knowledge of certain things, like the momentum and position of things, that these quantum fluctuations exist, and a universe can be created from them. Mathematically, it exists. He says there's no mathematics to it or something. Yes, there is mathematics. There's a paper that shows the mathematics. It doesn't mean it happened that way. It's not,
but
it's possible.
Yeah, and look at the Casimir effect, right? That's an example of a vacuum where stuff pops out of nothing, exists for a while, and annihilates itself without violating the second law, right? And that's example on a small scale of something coming out of existence. You get a particle-antiparticle pair. And as I like to say, as long as they annihilate each other before the energy auditor comes around and catches them, right? That you see this occurring, and in these experiments, again, go look up Casimir effect. You can see examples of quantum fluctuations and the actual physical effect it has. The net force that these virtual photons create on a particle can actually be made.
I think
this is not
Davies
some
that actually
mathematical.
Wasn't it? Davies was the one that actually he literally said, these things can exist and destroy themselves as long as they do it so quickly that we can't detect it. I mean, the universe does not want us to know.
Yes,
and
it sort of is. I mean, it's a nice way of saying
parable
it.
Kind of thing, right?
And so I was looking over the wiki page on Casimir effect, and it seems to be a reasonably correct explanation of the experiment and the forces.
Yeah, we see the force. The force exists, right? I mean, we can measure
and we can measure it, right? And so to say, oh, you can't get something from nothing. Well, the answer is you can. In fact, quantum mechanics, strangely enough, says you can't have nothing. You always have this sort of fluctuations.
You always have.
Now, I must admit,
energy.
As a kid, when I first encountered quantum mechanics, I was doing this. Oh, come on. The universe can't be that weird. No. And so I spent time as an undergraduate warring against quantum mechanics, saying, I'm going to catch quantum mechanics. I'm going to show that this stuff is just a mathematical thing. And I failed miserably. I tried I had some really nice, very simple, elegant experiments. Quantum mechanics beat me every time. So Now, of course, I'm much more rational about it. But
no, but I
my
find nothing wrong with
initial-
that. Good scientists will try to do that. I mean, we always have to test our theories, even confirmed ones, right? I mean, I think it's good that people go out of the way and go, okay, let's try to. But there's a fine line between honestly trying to find an exception to the theory and woo and crack pseudoscience, right?
Yeah. So my thing was, well, I'll design an experiment and see if I can find something that quantum mechanics says shouldn't happen. And so I work very hard at trying to falsify it. That's what you do with a theory. That's in fact, it's important for the theory. So people who say, oh, angels and headed pin created the universe. Well, that problem is that thing is not even wrong. It's not falsifiable. You've got to be able to be in a position of being proven wrong. And so I as an undergraduate, came in a lab and built experiments, for example, to take a single photon or single electron and send it through the two slits and measure where the thing impacted, right? And I would do that thing over and over again, and I would construct like these cubic sulfate crystals that had iridium atoms inside that would decay, and the decay of the electron would damage the crystal as it's going out. So I could see where the electron went out, ejected, and then I could detect it on the other side of the slit of where it came from. And I, in that thing, I was, and then look at the crystal and measure it, saying there's only one track that came out. We detect on the other side, so there's only one electron went through the slit, and I record where it is. If there was two or more, I would discard it. So I was seeing one electron at a time going through those double slits, and I didn't see shadows of those slits. I saw the interference. That is, the electron was interfering with itself, going through both slits. And but my professor was quite tolerant of that stuff because I was doing real science. I was trying to come up with a way to do it. And had I found a violation of quantum mechanics, I'd be really super famous. But no, I was unable to find a counterexample. So look up Casimir effect if you want to see about something out of nothing.
Landon, I heard that perhaps you had something to do with solar system formation modeling. Is that correct?
Yes, I've done some simulations on that, on solar system modeling. Although more of my simulations have been modeling on Jupiter and its moons. But
so I've got a question. I was thinking about why solar systems bodies have different compositions, the icy stuff further out. And I discovered part of the answer, which is, of course, that volatiles sort of boil off faster the further you get from the sun. But it strikes me that can't be the whole answer. So I'm wondering if you could comment on what other things affect planetary composition.
Well, if our model of how our solar system formed is reasonably correct, one of the things you might observe is that Jupiter is the big heavyweight in our solar system outside of the sun, right? That there's around 82% of the mass, I think, is in outside of the sun in our solar system is in Jupiter. And one of the explanations for that is a lot of Jupiter was formed from the hydrogen bubble that was popped or blown when the sun underwent ignition. When the sun began to fuse and radiation pressure pushes out the lighter material, the hydrogen helium, gets pushed by radiation pressure. The hydrogen helium that's not close enough to the sun to be gravitationally bound, right? The stuff that's beyond the edge. What do you mean by the edge of the sun? Well, it's the material that gravity can't hold on to, that radiation pushes out. That's how we decide you're in the sun or outside the sun. So when the sun began to fuse and the radiation shockwave went out, it was able to really effectively push nearby. But as it got farther and farther, its ability to push was reduced. And the bubble that it popped, if you will, was the line that Jupiter formed in. So most of Jupiter's mass of its hydrogen helium came from that bubble that was of the hydrogen helium that was not close enough to the sun to be gravitationally bound, that got pushed away when the sun switched on. Other heavier elements, irons, nickels, copper, so forth, that is most of what the inner planets consist of, had enough mass that the radiation pressure wasn't able to move it away, right? And in fact, there was this general settling going on of the heavier elements sinking towards the towards the center of the sun. The stuff that wasn't trapped in the sun was held at bay. So Jupiter, certainly Jupiter also acquired a lot of material from the asteroid belt. It's now our models of the solar system now state that the asteroid belt was never able to form a large planet because the mass of Jupiter was ripping it off. I mean, that even Mars itself is somewhat anemic in terms of it being fairly light and small compared with Jupiter. Excuse me, with Earth and Venus, but Jupiter ripped off essentially it destroyed the asteroid belt's ability to form a large planet. Had Jupiter not been there, it's quite possible that the material would have stayed inside the asteroid belt, and you've had another, Mars or Earth-like planet, but presumably lighter in mass, attempting to form there. The problem is if you don't have a Jupiter anchoring the thing in a nice circular motion, then you get all kinds of stuff tossing around. You get a fairly chaotic system. We think would result in harder for planets to stick around. But
so I have a question.
But that's probably not correct.
Can I just follow up? So
sure.
If I understood that correctly, then that would mean that the class of a star and the manner of its ignition would have a huge impact on the distribution and composition of planets?
Absolutely. And we see, for example, brown dwarfs, fairly low temperature stars, low mass stars, build planetary disks that are relatively close. We see the planets around those M-class low mass stars having relatively tight orbits, in part because the radiation pressure of those things doesn't have the bubble set. And so one of the things that's being tested is I think what you're implying is, okay, we should look at these extrasolar planets around other stars, and look at the type of star and see, do G-class stars able to pop a bubble and form a Jupiter, whereas something like a brown dwarf, a red dwarf, doesn't have a Jupiter? And so far that seems to be the case, but we need more data to confirm it. But that's certainly something which the data hasn't falsified yet.
One question I was wanting to ask is, what do you think about the possibility of finding planets that are like Earth and that they could sustain human life or human-like life?
I think it's a pretty good chance. I mean, we now have a number of candidates of planets that are in relatively stable orbits, whose temperature zones are not too hot if there's water, it wouldn't be boiling, it wouldn't be freezing, it'd be sort of so we do see Earth-like masses. There's a wonderful star which is discovered to have 7 planets around it, 3 of which were really in a nice Goldilocks zone, and they were near Earth mass, and the temperatures. In fact, one of the temperatures, the typical temperature of this planet was something nice 15 degrees Celsius. So we are seeing, just from our limited sample of about the last 1,000 light years or so, a number of Earth-like planets there. Earth-like planets are harder to detect than the big Jupiter masses. So our planetary distribution is kind of biased by the ones that are really obvious, the big ones. But as we get better at detecting them, we are starting to see lighter mass planets. And based upon the statistical data we have now, we can say a couple of things with reasonable, plausible certainty: that planets outnumber stars, that rocky planets outnumber the big gas bags. So in a galaxy of 200 billion stars, there is at least there should be at least 1 trillion planets orbiting stars. That about 70% of the stars that are singletons, like our sun, have planets around it, and 30% of binary or multiple star groups have planets around them, which surprised us because we thought that binary planets had too complex of gravity fields to be able to form and great stuff, but obviously you're wrong there too. So so the most common type of planets appear to be the Pluto class, the dwarf planet, and Earth, super Earths are kind of like the extreme of the rocky planets, and those seem to outnumber the Jupiter, Saturns of the world, and planets outnumber stars. So just given the combination of stuff out there, it's you know, I think are in relatively safe ground to say that there are probably a lot of Earth-like planets out there. Whether they have the water and the nitrogen, the carbon in a stable like form in a nice temperature so they can get complex chemistry and a perfect replication, called evolution, or not is another question. But the next generation of radio telescopes, the next generation of space telescopes are going to give us the ability to begin to not only image some of these planets, but to begin to look at the composition of these planets, begin to look at the next generation X-ray stuff. We're going to be able to detect X-rays from the lightning, right? What I think will happen in our lifetime, or in your lifetime, will be it'll begin with controversial claims of, look, here's a planet. It has a nitrogen atmosphere. It's got oxygen atmosphere. It's got water molecules. It's got very complex emission lines suggesting there's complex molecules that form the atmosphere. We detect lightning. It's got auroras. It's at a temperature where it's not cryogenic and it's not boiling. Gee, that would be a nice comfortable place to have some chemistry go on. That's going to be the first class of stuff. And then eventually we'll get direct imaging of planets where you can look at stuff in the atmosphere and find, you know, rich chemistry going on. Again, what we call imperfect chemical replication. I'm not saying it's going to be DNA-like, but you'll find that you've got some rich chemistry going on. There's energy source. It's not turning into plasma where it destroys the chemical bonds, and it's not cryogenic in form, but you have some energy there to do interactions. The chemistry is complex enough that it's not simply just sodium and chlorine get together to form salt. It's actually evolving, right? And that's one of the things you want to see. When will we actually detect a civilization? I would find it really shocking if we had the only civilization around in the universe, let alone the galaxy. But we haven't yet detected it because it's hard. It's really hard to detect a planet around even a nearby star. So detecting their version of I Love Lucy, TV shows coming to us has to wait a while for better detection. But that day may be coming. Right now, what do we know? Rocky planets like Earth are relatively common. They come in a wide variety. They're around a wide variety of stars. And the odds are that there are plenty of Earth-like planets. The question is, do they have the right composition? And are they stable in stable enough orbits? They have a nice Jupiter anchoring there so everyone doesn't go all off in kilter, but they stay in their nice temperature zone so that the chemistry can evolve and do something interesting, like form a bunch of people to sit around a YouTube, Google Hangout discussing the universe.
I would be happy with if we even found just the most rudimentary life elsewhere in the universe. That'd be good enough for me. But I get to ask the last question.
But that's why.
Go ahead.
But that's why things like the Square Comet Array Telescope that's being built in South Africa and Australia is important. That's why the James Webb Telescope is important, because those telescopes are going to give us the ability to do some direct observation, to be able to take spectra of planets around other stars. An amazing feat, but that will begin to sit there and say, look, that certainly looks like complex organic chemistry.
Be awesome. It'll be so incredible if that ever happens. But I get to ask the last question because I do got to bring this to a close. This one might be a little bit technical, okay, so bear with me here. But if you took all the Mr. Intelligence Design's books and you put them in the same space, could that form a supermassive black hole due to the density of wrongness?
Well, I think the problem is you'd have the zeros and ones would kind of overlap each other, and you'd have probably this Q dot thing where it would be oscillating between 0 and 1. I mean, it'd be an interesting question, and maybe Red Eye could sum up the binary of
Red
his
Eye's
book
he's
to
still,
tell us whether there's more zeros or ones in his book.
Well, he's still suffering
But-
from having read his book. So I, mean, I think Red Eye needs some time, a convalescent time. I mean, you could just kind of see his writing is shaky, and you know, if he was on air, you could tell his voice would be kind of quivering.
Well, he has other things, like he was just talking last night about, you know, chasing out a 1.5 meter python out of his garage because, you know, he lives in Australia where things are different.
Still not as dangerous as Mr. Intelligence's writings.
Well, Red Eye just rolled his face across the keyboard because Mr. Intelligent Design told us that gravity is in fact, folks, and this may be a shock, a bunch of photons squeezing together. He calls them squeeze-ons.
Oh,
but gravity, electromagnetic. I mean, we squeeze electromagnetic radiation all the time. It's, you know, like lasers, but I don't see gravitational forces running around these lasers that we build in. And you know, I worked at a lab where we had one of the largest lasers in the world. That at that time was a Shiva laser, and we didn't see gravitational fields being formed when the laser was trying to do fusion. So that seems a little bit.
Are you saying that his
implausible.
hypothesis has been disconfirmed? His conjecture is wrong. Like
it doesn't seem to be
wrong?
there. But I think fundamentally his problem is that he believes he has a truth and he's trying to rationalize it.
Right.
He's not going through a scientific method of asking questions and beginning to falsify it. If he said, I do not believe in intelligent design, I'm going to go through the process of proving there's not intelligent design, then we would have a much more scientific discussion. But he believes he's right. And it's very difficult to argue someone out using logic, to argue someone out of a position they didn't use logic to get in the first place. So he believes he has truth because of his faith, because of whatever, and he's trying to rationalize it. That's not the scientific method. Scientific method says, here's a hypothesis, it is falsifiable, and I'm going to do my darndest to prove it false.
Oh, I couldn't agree with you
That's
more.
the scientific method.
Couldn't agree with you more. But anyways,
So
everybody,
that's why he's not scientific. That's why he's not a scientist.
Yeah,
in scientific
he's calling
method.
himself a scientist, but that's an abuse of the word.
But he's not exhibiting the scientific method, so it's hard for me to give him that credit.
What I want people to do is, like I said, you know, Landon, we would love to have you back. I'd love to have you back. And if people want to like message me specific topics they think they might want to narrow down, whether it be like somebody had mentioned like the Higgs mechanism we could talk about, or somebody like, you know, if you want to talk specifically about black holes, I love black holes, right? So I mean,
or primality testing, or Antarctica, or
you name it,
or you know, geology, or you know, that sort of thing. It's fun to.
Is there any subject you don't like? You seem to be pretty well rounded in the sciences. I mean, you're one of those people like myself. Just any kind of field of science holds an interest.
And by the way, I'm not saying that the Big Bang actually happened. If you look at my words, I say if our model of cosmology is reasonably correct, there is evidence to support the Big Bang, and it has not been falsified.
Exactly.
That's a very different thing. And again, you really do need to understand the scientific method, and it's hard to do it if you come with truth that you claim is from God, that is, and everything else that violates it must be wrong. Then you're not in the scientific method. You're better off in theology.
Well, the problem is again, if he can't falsify something if he doesn't know the rudimentary aspects of it. I mean, he doesn't know anything about Big Bang. I mean, he didn't know anything. He says he's a civil engineer, and yet he said he'd never taken a physics course. He said he had years of math, and he didn't know what the derivative of x squared was.
So a civil engineer might be trusted to, let's say, design a road overpass, but a civil engineer is not someone I trust to develop models of cosmology. Just as I am not a physician, so you do not trust me to design treatment for your heart condition, right? Same thing, I do not ask a civil engineer to go and discuss the formation of planets. You're better off asking a planetary scientist.
How do you become a civil engineer if you've never taken a physics course? Because he says he's never taken physics. He didn't know what the derivative of x squared was. I would think I know people that are civil engineers. They take a lot of math, and that should be a gedunk question. What's the derivative of x squared?
I mean, because in engineering, you have to do a lot of stuff with mechanics, which is physics. You have to deal a lot, engineering that's doing electrical has to deal a lot with electricity and magnetism. It's hard for me to conceive of an engineering discipline for which physics is completely divorced of stuff. Even stuff I use in computers, right?
You don't even have to give him that much credit. He didn't even know what the hypotenuse of a 3-4 right-angle triangle was.
No, that's for Gizmo. Spurs didn't know.
No. That was Mr. ID.
You didn't know either?
You thought the integration of what was it? Or no, the differentiation of x squared was 0.
Yeah, that's what I'm saying. He didn't know, and he didn't know Hooke's law, which I was like, okay, wait a minute. I've taken metallurgy, I've taken physics. I guarantee it, any civil engineer is going to know Hooke's law.
Yeah. Now, to be fair, if you asked me to do something like derive the Boltzmann distribution,
good grief,
off the top of my head, I would sort of flail around and say, yes, I did that once. I passed my test. But there are some fundamental things that again, engineering requires knowledge of physics because of mechanics, because of electronics, because of pressures and temperatures and other things. That
area under the curve, man. It's all about the area under the curve.
Integration.
Yeah. So it's possible that someone might get a degree and be weak on something, but it would just be, I wouldn't, again, I'm not positing stuff because I don't know about Mr. Intelligent Design, background. So I can't say he's not a good engineer. I'm just saying that engineering requires at least knowledge of physics.
I just outright say that he's lying. But I mean, you can't be an engineer and not take physics courses.
Can I ask a positive question?
But I have to say this, Mr. Intelligent Design, to confuse something as massive as Pimplunk with something as dainty as Jacqueline Glenn suggests your powers of observation are suspect.
I've been trying to get Jacqueline Glenn in here, so if anybody can reach out to her, I mean, she probably gets inundated with stuff, but I would love to have her as a guest. Not the fact that she's hot, well, kind of, but
I'm just going to make cheeseburger jokes.
I like her. What can I say? I mean, it is what it is, right? But I mean, I've tried to reach out, but again, she doesn't follow our community, But anyways.
But anyway, so my invite to Mitchell Design, if he comes on your show, is to have him come in with methods of come with a scientific method and explain how you could do an experiment to falsify his concept.
Oh, we bring him on every week. It's the lull entertainment hour. Yeah, he's a regular. I mean, it's comedy gold. I can't. Yeah.
But I if you ask me, in my opinion, I agree with Laplace. I have no need for that hypothesis in explaining the universe. This is the thing that allegedly the legend is that Napoleon asked Laplace, why, where is God in all his equations?
Yes.
And he says, Your Honor, I have no need for that hypothesis. Same thing. Mm-hmm. Physics has no need for the hypothesis of God. The out of the laws of physics, you get a universe.
And it's fun you mentioned that because that's the position I'm going tomorrow. When I have a debate tomorrow with an intelligent design advocate. As a matter of fact, it's supposed to be the debate of the year. And I'm going from that very position.
Good luck.
I'm going from that very position. Even with an intelligent designer, it doesn't matter. It doesn't change the fact the model works. It doesn't change the fact that the best explanation for systems of nature are the models we have, because positing an intelligent designer doesn't get you anywhere. It has no explanatory power, has no predictive power, and it certainly is not a better explanation, abductively reasoning or not. And
as Paul says, it's not even wrong. Right?
It's not even wrong. Yeah, I mean, exactly. Wronger than wrong. So, I mean, I'm going from that exact position, and I might even quote LePon's thing on there because that's actually so true. There's just no need for it. The intelligent design is not factored in when we take into account the fact that gravity exists because of curvature in space-time. I mean,
it's because we tend to see something complex and say, oh, that must be a tool that was made, and there must be a maker of a tool, right? And that's kind of our how our thinking is. But just because you go out in nature and find something they can use as a tool doesn't mean a tool maker made it, right?
Absolutely.
It's so. But that's my opinion. And to say it's
and I think most of us agree.
Again, I don't mean any disrespect to the person. I certainly the videos I saw that Red Eye thing were entertaining, and again I'm still I still am a patron of both Pimp Monk and Jacqueline, and I find that mislabeling is just that's funny, and you provided a lot of humor, so thank you very much for that.
And speaking of which,
Mr.
on that note, because we are in the 3-hour mark, I want to thank everybody for listening. I really appreciate you coming in and engaging with us. We love having these conversations with articulate, educated people. One of the reasons I do this, as people know, is that I obviously have a Patreon myself, and I have PayPal, and this is how I actually support myself. We have a great amount of people in the support community that has been supported my channel, Red Eye even being one of them. And if you guys find these things entertaining and informative, I again, like to ask, to become Patreon, and even if it's $1 a month. I am one of those people that I'm grateful for everything. People have been so awesome.
I donate $1.
You do donate $1.
Yeah. Let those dollars quantum tunnel from your bank account to his bank account through the means of magic of Patreon.
The magic of Patreon. It's funny, and I haven't mentioned it before. If I really wanted to make some Patreon, I would become a flat earther. Those guys make bank. Wow.
Yes.
Oh my goodness.
But again, and I apologize for the things I got wrong, and I hope I gave people some food for thought, even if you don't agree.
Oh, I think you're actually probably going to go down as one of my more favorite guests. So take that to heart. And again, I wasn't kidding. I would love to get you and Hugh Ross on. Unfortunately, with Hugh, the problem is that he does a lot with reasons to believe, and it's very formal with him because he has a image to protect because he's the founder of Reasons to Believe. And so when he comes on, it's a lot more studio-like. He can't do these informal things, and which is a shame because I would love to get him in a much more informal hangout. Have you talked to him before, you Ross?
But
real nice guy, just an awesome nice guy, But we've gotten him, we've gotten PZ Myers and Aaron Raw and Mary Schweitzer. You know who she is, Dr. Mary Schweitzer. Yep, yeah. We've gotten her on, which is very.
You might want to also approach is King Crocoduck.
Oh yeah, no King. Oh yeah, no, King is awesome. He's been in my head many times.
Have you seen some of his stuff he's done on quantum mechanics? Yep. And they're really great stuff in there.
King and I talked quite frequently. He's been in here many times. Yes.
So big fan of King Crocoduck. Top respect to the guy, and I wish you well on your studies.
Do you have a hangout? I mean, have you been in a hangout with him? Because I can get King in almost any time. I mean, so anytime.
Oh yeah, I mean, and we've hung out in person as well. We've done sort of science stuff, and I. He is going to be a really great asset to the physics community. He explains things and very, very well.
He's so good.
And I think he's probably started off accepting quantum mechanics more than I did, and this is why he's a much better.
Oh man, I saw he on the other day. Well, I guess it's been a month or so. He messaged me some of the math he was doing. And I've seen some complicated math because I had to do some nuclear stuff. I have never in my life seen the stuff. I mean, again, it was like nothing you could. I like, what is this? And I go, okay, look, I know what a del is or a Hamiltonian operator. I can tell a tensor formula. This was mad. This is like you should look like Hogwarts. Seriously, It was like, what is this RuneScape? I don't know any of this. He's like, don't feel bad. I don't understand either. I just learned it, regurgitated and.
And again, in humor, one of my evidence against intelligent design is that no intelligent design would allow quantum mechanics in a universe. It's just too weird, right? Yeah. If I were designing a universe, there wouldn't be quantum mechanics because
that's your entire fudge factor for the universe. That way it's so unexplainable. But anyways, I am bringing this to a close. Landon, thank you very much. This was amazing and awesome, and I hope everybody who views this comments and likes the video.
I take privacy too serious online.
What do we got? We got what was this, G-Man?
Oh shit! Yeah, sorry. Yeah, I gotta do.
G-Man infiltrated another one of my hangouts.
No, he just started a hangout called Outside Chilling, and I was like, what the? He's talking about dot dropping people. I'm like, oh my god. Okay, he's on his bike.
We're gonna have an after show, so anybody who's interested to talk about this, or you want to?
Okay.
You're gonna change.
I mean, I was gonna ask you if you wanted to host this since it's your guest.
Have it on your channel.
No, I really, I kind of don't want to.
Oh, okay. Oh, okay.
Unless you really,
But
really
you know
don't want
what?
to,
Even
then
though
I
there's one on
will.
his channel, everybody who you've not subbed to Dragnaut, go to his channel and sub to him.
Don't sub to me.
Yeah,
I'm
sub to
just,
him.
I'm
He
sitting
does
here,
good stuff.
I'm doing genetics homework. Fuck you all.
But anyways, I am ending the stream, and I want to thank everybody who's listening. And like I said, please leave a comment. Please like, even if you can't be a patron or support, you do support me by watching, and you do support by leaving comments. And I want to thank
And
you all.
please ask questions. Please ask
Lots of questions.
Well, and what we'll do is, if anybody messes me or puts it on G Plus questions that we might bring to Landon's attention next time he's on, we'll get a list going. Okay, sound good, everybody? Awesome. And
Hell yeah.
Yep. Everybody enjoy your weekend. Enjoy your April 1st. And by the way, I apologize sort of for my April 1st prank this morning, but I got you guys good.
Yeah, it was a nice day. And happy April Fools to those down there. And the universe is returning back to normality. In fact, I was talking with the folks down at the South Pole, and they can see the section that's no longer April Fools, and it's normal now. So
normality has we've reached normality again. Or at least our definition.
Bistramatics.
Yes. Thank you guys. Thank you all for watching, and we'll bid you guys adieu.